Welcome everybody to the third day of the workshop. Today we will have the discussion on open data, and after this first session we will also have a very interesting panel discussion. We again have a discussion session after the first session today. So if you have questions, please use the forum, use the Q&A box, ask to speak, and we will take your questions, and the speakers or anyone else may answer them. So this is all very exciting new information that we want to discuss. And it's my pleasure now to announce the first speaker, which is Eckhard Elsen. He was the Director of Research and Computing at the CERN, while the open data announcement was made in December last year. Now he's back at Day3 and he will tell us all that we want to know about open data. So Eckhard, the stage is yours.
Thank you, Oliver. I'm trying to share my screen here. Hope this works.
So we can see your screen and we can also hear you.
Super. Okay, let me try. Unveiling hidden secrets. Well, that does require openness to start with. And openness has been the topic of many a political discussion over the past years, in fact, over the decades. So I will try to illustrate these points a little bit and then end with the conclusions we drew up at the end of last year and discuss that a little bit. So open access to data, I mean, it seems trivial. Public research is funded by the taxpayer, and hence the data should be available to everyone, or at least to each taxpayer. That sounds trivial. You pay for it, you got to get something. So let's see where the subtleties are. The benefits of open data are very obvious. If data is freely accessible, more scientists engage and contribute to the interpretation of the data. You have the advantage of not only seeing a experimental particle physicist who has engaged in QCD studies, so a rather narrow view. You can really draw on the experience of multiple disciplines and learn from their methods of analysis and get a broader view. The tools that are available in other communities can be reused and applied there. We have seen this in a big way with the machine learning. And you would also think, because you basically allocate the entire brain power of the world behind the data, the analysis feedback should be faster and hopefully even be more profound. So it should be quite natural that everyone, that data are open everywhere. Now, there are some downsides, and I think we've gone through an area in which we all know what false scientific claims mean, and they are not always easy to rebut. It does take some effort to really rectify false statements. I mean, this may be an innocently made false statement because of incomplete understanding of the data, but it may be even on purpose. And if it's done very cleverly, it does take a lot of time to rectify it. So there's a price to pay. Who is paying for the effort to go that is necessary to correct the data? And by the way, who will be blamed? I mean, it's the group that built the apparatus in the first place, and then, of course, since it's data of the experiment XYZ, those people will have a reputational damage. It goes further even because the progress really comes because the progress in building these experiments and conceiving the experiments, resolution, to improve the resolution, you need to have something that makes it better. So you really depend on the ingenuity of the instrument builder. And that may not be properly recognized if they are not engaged. So pouring out the data into the open may not be the best thing to do. And then also it's clear the experimental exploitation may be incomplete because of lack of familiarity with the tools to analyze the data. But data should be available to everyone. What is really behind it? Now, even a taxpayer may have a second thought. Let me call it pride, be it national, be it local. The community that funded this effort may attach some pride to it, but also some real justification for why not disclosing the information. Can they draw advantages? And if you look at that, commercial advantage often comes from an advantage in knowledge. And so if a local community knows more through its research, that through the research it funded, why should it give up this advantage for any odd reason? This is this may sound complicated, but if you look a little bit what has happened over the last many decades, when we look back 70 years almost, the progress in research really happened in the big companies. Dell Labs, IBM Research Labs, those were centers of excellence, and they were funding the research to make progress. This was privately funded research, and they were attracting the best people around. Now, that has changed in many ways, and today the big companies at least always have a clear view on the commercial benefit. And so the progress in research and private research is outsourced to startup companies or to universities. And universities are again publicly funded. So in some sense, the work that in the past, the privileged work of research that in the past was done in companies now is publicly funded at universities, and often our funders, our public funders, suggest or encourage collaboration with industry, knowledge transfers, and all the buzzwords behind it. De facto, one has to be very careful not to give an advantage to a specific private company and given a disadvantage to other by hiding or not sharing the knowledge. It's a tricky question of sharing the societal load, if you wish. So each society, I think, has made a decision on what to support and what to fund. And I think this is particularly true for fundamental research. For fundamental research, because it does not, at least usually not, lead to immediate commercial benefits. The observation of electromagnetism, the real application we now use every day by using the phones, but 150 years ago it was not so obvious that anything could be done with radio frequencies and radio signals. So fundamental research, we live in a privileged realm as long as there is interest. And I must say, I find it very surprising and encouraging that in fact the drive to carry out fundamental research actually comes from the society itself. You see it in school kids. Wherever you go and you speak about stars or speak about fundamental particles, things you can't see or grasp immediately, raise such an interest for those who are keen to learn more. And I think this is really the benefit that we have. There are students and people at large do want to understand just for the sake of knowing more, and that is really driving us, and it's an advantage for us. There is not immediately a commercial interest, and that's very good. I would rather consider this our field as a cultural incentive, and so that the society may make a choice of what kind of fundamental research to fund. But if it doesn't happen at all, I think the society is intellectually a purer one. It's a little bit like a society without art. People like to dream and take it further, and that is important and makes it easier when you think of open data to release the data and share it. Now, we discussed the taxpayer point, or the point of view of the society. For the researcher, there's also a point of view, because the progress is driven by theoretical understanding, of course, or by theories in general that need to be falsified. But on the other hand, also by progress in instrument building. If the resolution can be increased by a factor of 10, it often reveals new features of the fundamental observation. And it's actually a competition between different approaches, even on the instrumental side, to arrive at the best tool for exploration. And that doesn't come for free, because before you really arrive at that resolution, it does take a tremendous dedication of the team of scientists to construct and actually optimize the apparatus. And I think in the recent past, we've seen examples of these. LIGO, it took decades to arrive at the resolution that allowed for observation of gravitational waves. I think we can take the LHC experiments. They already have a history of more than 25 years, and I bet they will go on for another 25 years before they close down. And likewise for satellite instruments, the preparation of that is enormous. So it does take dedication of the individual researcher. Now, you can have two approaches in profiting from the open data. And one is a complete separation of building the apparatus and carrying out the analysis. And there are fields of science that have chosen to do so. Astroparticle physics, for example, where a team of instrument builders develop and operate the next generation tool, meeting all the constraints of having a satellite-proof experiment. And we've seen this with the CMB satellites. We've also seen this with the Fermi telescope. Even though Fermi telescope was already a bit of a mix, so they didn't release their data immediately. I think they have a grace period of a year before they open up the data. But when we look at the data is really a map of intensities of some electromagnetic signal over the sky. And this is really all the information that is there. So everyone can develop his own filter and analyze the data. And this is why it is fairly straightforward to release the data. Let me use that word, dump the data on the public community and have it interpreted. The other solution I think we are more familiar with is the LHC physics, where the instrument builders develop and operate the next generation tools for many decades. Collaborations are the owner, or if you wish, the custodians of the recorded data, and they know exactly under which conditions the data have been recorded. And it's very detailed knowledge. It's very difficult to even write down what the circumstances of all of this is. And this mammoth task of triggering, calibrating, and analyzing the data before you arrive at the full vector, that is very complex. And what is worse, it's even very difficult to explain the detailed features of the recorded data to a lay person. What does it mean if the ADC count in this channel is twice higher than the neighbor, even though there is no signal? Do I have to worry? Is it broken? Or is it a feature that can happen because there was additional light that I have to take into account. So this subtle knowledge is difficult to share. And so there's a cost of openness in the data for fundamental science. In addition to building the experimental apparatus and the recording data, the data have to be prepared in a fashion that is acceptable to the occasional user. So they need to be aggregated and reduced to the physics information. And you can already understand that when you take such shortcuts of compressing the data to the simpler information, you may lose some of the resolving power. So what has happened at the LHC? First, there's a long history of being open at CERN and everywhere. The first drive, I think, came from the open access policy, which is also now fostered by the European Commission with the open science policy. Openness is now required in almost every grant application. You have to lay out how you share your data after you've taken it, and even how you preserve the data afterwards. So what we did at CERN in 2019, we installed an open data policy working group for the LHC experiments. And they very quickly recognized that there are various levels of openness. And I've already mentioned the trivial one, which is the publication. So the result of a tremendous work inside the collaboration that leads to the 4 pages also in the letter that is finally published. And the fact that these letters are now open access for more than 95% of this LHC publication, I consider a huge success. This initiative, Scope 3, of making the data open is already now in its 3rd round and is a tremendous success. In fact, it's an example for other communities who are not as coherent in their approach and in their quest for openness. So I think this is established since 2013 or so, open access to publications. Now, there's a bit more to it. We've gotten used to releasing also unbinned n-tupers, let's say, or vector size data, which often then end up, I guess everyone is familiar with the Durham database for accessing sort of raw data of a histogram of a scatter plot and so on for later digestion. So that's already a little step towards open data. And then since the beginning of the LHC, there has been open data for outreach and education. I'm sure many students already have discovered the Higgs particle themselves by sifting through this data to understand the features and extract the signal. So that has gone through the open data portal at CERN, which has grown in the meantime. I'll give the link here on the right. The open data CERN-CH allows to access open data from the LHC experiment and even more. So that's the so-called level 2 data, and what we are really concerned about is level 3. Level 3 data, which are suitable for physics analysis to a large extent. Let's say it's one incarnation of 4 vectors for each event. So you read an event and the 4 vectors with some assumption on the particle species. You will realize if you consider a jet a quark, do you then call it a quark, or do you go to the level of the individual particles? And you immediately feel the ambiguity you have in assigning a property to a final state object. This is why the experiments really speak about objects and not about particles. But anyway, you can choose to have one incarnation of these objects as particles and make that available for analysis. And that's really what is driving the open data initiative at CERN. Because the next course, the next final level would be the raw data. That is which ADC fired at which time, which nanosecond that is, and what was the beam intensity at this moment, and all of this. So it's very detailed knowledge, which to first order is impossible to understand unless you are an expert, or maybe an expert inside the collaboration. I should say here that even large groups of the collaboration itself, let's take Atlas as an example, would analyze at this level and not go to the raw data. It's only when you try to extract new features that require new analysis method. So here it is. Sorry, it's a very fine print, but I'll give you some aid in going through the open data policy document that we then arrived at in discussing between the 4 experiments. And I really would like to acknowledge the openness, to use that word again, of all the collaboration in advancing this topic. So if you read this document, you may not be able to recognize this on the screen. Level 1, level 2 data is discussed, and level 3 data is this shaded region. And it speaks about several things that are necessary. It's not enough to just release the data. You also need the algorithms to analyze the data in a meaningful way. So data and algorithms have to come together. It's also clear that the experiments would like to have the first go at the data themselves and see whether they can extract new features, for which then, of course, the collaboration would claim discovery. And that does take time. It also does take time to calibrate. It does take time to actually allocate enough data, luminosity, so that you have a meaningful run period. So a latency of, let's say, 5 years order of is something that should be respected before the data are released. And then it's also important that the intellectual property of the experiment is preserved. And so this is, it does require proper reference to the originator of the data, to the collaboration. It goes by the Creative Commons CCD waivers, and the data need to be identified with the persistent data identifier. You can read this, in other words, so that the experiments are properly acknowledged in their effort. And then there is a disclaimer that the whatever claim is made, and even in particular wrong claim is made by using the data, it cannot be blamed on the experiment. It needs to be done by the experiments themselves. So this is a disclaimer on the limits of that responsibility. Now, I have put to the right here some statement by a body that is existing at CERN, the Scientific Information Policy Board, composed of representatives of many experiments, so not only the LHC experiments, who actually welcomed this document a lot, and they endorsed the open data policy and hope that CERN is driving or extending this also to the other experiments, let's say the fixed target experiment, the rare decays experiment, and neutrino experiments, you name it, so that it really becomes a common aspect of all the research. So this is really the document, the general document. It goes by an implementation document that varies between the experiments, and the variation is largely the latency between data recording and releasing the data, the amount of data that is released. And it's clear this needs to be specific because you can take heavy ion data under very special conditions that can be maybe released rather quickly once they have been analyzed, and you have other data for which you need to record more. Heavy quark data may depend on a channel that you want to release, let's say charm searches or so. And for searches for Atlas and CMS, of course, they would like to discover the supersymmetric particle first before releasing it. So they need to accumulate some statistics before they hand it out. So each experiment has drawn up a specific document for that. The structure is very similar. The details are somewhat varying, but they all follow the general policy that I alluded to. So this commitment to openness is somehow entrenched in the spirit of working at CERN, or in particle physics, I would even claim, where we work in global collaborations, share the data anyway. The collaborations have a size of a few thousand, so it's shared among these people. The step to sharing it with another few thousand is generally not so long. So this belief in the values of openness and collaboration is driving it. It has resulted in major discovery, the sharing of building an instrument, operating it in the best way, and analyzing in the most ingenious way is really a feature of these large collaborations, and that really paid benefit. And by the way, and this is just a side remark, when we looked at the working group, even for COVID-19 pandemic research, the sharing was immediately evident. So open source is another feature of the openness. And you know this from the web that was invented at CERN with the goal of optimizing interaction. And that's exactly a feature of the openness. So open source is another way of fostering progress in a very efficient way. And this is why we are committed to it. So what has been paid, even as a tool by the public, should be made available to the public. And this is, I think, one of the reasons why these open source repositories are so popular and successful. Open access, I mentioned this already with the Scope 3. So that was formally introduced in 2014 with the open access policy, and Scope 3 is now really the official incarnation and has been accepted for our field to a very high degree. Open data, that was really the purpose of my talk here. The open data portal, which shares already several terabytes of LHC data. In fact, we are arriving now at a petabyte with the recent versions. And the applications are, of course, test of a theoretical model, theorists sitting in, what shall I say, New Zealand, to have one of the points that is farthest away from CERN, would like to test a crazy idea and see whether it's borne out in the data. And so that is clearly something that should be possible. In fact, the first PhD theses have been made going this way. So the other feature of having this data open is they can be run through machine learning procedures, and these machine learning algorithms can be optimized. So this open data policy has been concluded for the LHC experiment and will be extended further. And I think it's very obvious. CERN is committed to support openness for publicly funded developments at all levels. And I mention it here again, and I think we can be fortunate to be part of that branch of science because it's not so straightforward in other fields. And that almost takes me to the end because there's a corollary which has been a concern everywhere. Once you release data openly, it's something that is out there and can be interpreted. It's always, it just needs to be maintained, maybe copied because a new carrier of the information comes around. But it also, in this sense, naturally leads to data preservation on the long run. And that is a concern when the LHC experiments in I don't know how many decades will dissolve. we still would like to be able to look at the data in the year 2100 and analyze some of its features. Okay, and that takes me to the end. Thank you.
Thank you very much, Eckhard. That was a very nice and interesting overview. We have now the next speaker coming up. Before we do that, is there an urgent question in the audience? Someone wants to make an immediate comment to Eckhard, to the subject? We can discuss everything later also in the discussion session, but if there's an urgent question right now, we can take it. Seems not to be the case. Then thank you again, Eckhard. Then I would ask Tibor to show his face and also share slides, and let me quickly introduce him. Tibor is a senior computing engineer at CERN, and he is leading several open and reproducible science projects there. One notable example here is that he's the founder of the CERN Open Data Portal and also of the CERN Analysis Preservation Framework and many others. So he will have many interesting things to tell us, and it's a pleasure to have him here and to listen to his interesting information. So Tibor, the floor is yours.
Thank you for the introduction. So I would like to offer you a perspective from the CERN Open Data Portal inner workings to speak about the data stewardship task and the maintenance of the portal, basically complementing the talk by Professor Elson. So CERN Open Data Portal was born in 2014. It was launched by CERN Information Technology in close collaboration with CERN Scientific Information Service and the representative from LHC experiments. So the content is very rich: collisions, simulated datasets for research, derived datasets for education, but also accompanying documentation, virtual machine software tools, which you will see in a minute. So current size in March, it has actually grown a lot. So close to 8,000 bibliographic records, close to 1 million files, and close to 2.5 petabytes. So education-oriented use cases are basically coming into high school teachers, high school students, university students. So the portal is offering interactive event display. On the left-hand side, one can see an event in the CMS experiment, Daimyon event, and on the right-hand side, basic histogramming to basically look inside the derived datasets and try to learn about particle physics. And what is most interesting for this audience is the research-oriented use cases. So we are offering the virtual machines to have basically the similar experience as the experimental particle physicists have in analyzing the data. On the left-hand side is the ALICE virtual machine, and on the right-hand side, it's a simplified but realistic research-level analysis of the Higgs to 4 lepton channel. So some of the last news from the past year. So what happened in August, CMS experiment has finished releasing 5th batch of the open data, which completed the proton-proton collisions recorded in 2010, 2011, basically in round 1. First half of 2012 is also available. Then later, the CMS physicists have run a workshop for theorists as the LPC, basically providing a lot of examples how to work with the data, understand the content. So if you are interested in deeper knowledge, there is a Indico page and lessons to have a look at. And last news in December, there is a first heavy ion samples which were released by the CMS experiment from run 1 together with the associated reference proton-proton datasets, something like 200 terabytes. So all this research level data enables independent theoretical physics research. On the left-hand side, looking at the INSPIRE, there are now over 30 papers citing CMS open data released on the portal, which is searches, jet studies, machine learning, and the CMS collaboration basically cites these independent studies themselves, which is very good to see the knowledge spread or sharing going the full circle. So this is all thanks to the work by the LHC management boards on data preservation and open access policy. So after a certain embargo period, data is released to open, as we have heard in the previous talk. So now I would like to walk you through some of the internals of the portal from the fairy tale perspective. So FAIR obviously makes a reference to the guiding principles for scientific data management, which were published now close to 5 years ago. So FAIR Data should be findable, accessible, interoperable, and reusable. So let's try to have a look how the CERN Open Data Portal handles these topics. So from the findable perspective, all the data and metadata should be uniquely identified, and for humans and machines. So there is a global and persistent identifier. The metadata should be rich and indexed in a searchable resource. So example on the left-hand side is one of the primary collision data sets from 2010. All the records on the portal are exposed. You see the URL in the bottom as opendata.cern.ch/record/some ID. So this is our record, bibliographic record identifier. And some of the research data sets have also minted a DOI for citation purposes. So basically all research level data sets, collision simulated software examples have a DOI, but we don't do minting for everything. For example, configuration files or documentation is only having a record ID. And what is available on the left-hand side for the web peruse is available also for machine readability through custom JSON schema we are exposing. So you can see the dataset is described, linking to nodes for validated runs. There are technical characteristics, how many events, files, and terabytes it contains, and system details, which CMS software version is recommended for analysis. But we are having rich context description about the data sets, how the data was selected, how it was validated, and how one can use the data. This is also available both on the web and through JSON. The aim is to provide very rich context information so that even non-specialists could understand and work with the data. If there is some information which is not possible to store in a record, there are detailed guides provided. An example is the CMS Global Tag Condition Database. How would you like, how could you work with it? So there are several of these guides published on the portal as an associated documentation guides. For the information discovery, we have a rich facet interface. On the left-hand side, you can see various data types available: dataset documentation, environment, glossary, news, software tools, analysis, and supplementary configurations, which is also available to machines through the REST API. So I would say from the F point of view, we are fulfilling all the necessities. So let's move to the accessible. Basically, metadata should be retrievable by IDs. Protocol should be very free and open without any authentication and authorization. So content can be downloaded by simply browsing and downloading files manually from the portal. But of course, this would be a huge work if not to download all the 1 million files. So another piece of news, last year we have released the little command line utility, CERN Open Data Client, which can be installed from PyPy and used to work with the data in an automated manner. So example, how to download metadata information. On the left-hand side, we can see some of the functionalities of the client, identify file locations. So if I would like to know, for example, for the DOI Open Data CMS ZVT8 MSENA, what is the data size? There is one command line instruction to call to give the exact, to access the JSON ports, which has the size information, and to have an exact byte value in advance. And on the right-hand side, there is a possibility to get file locations, for example, for this Higgs-2 4-lepton example, which is record ID 5500. So we are seeing these are the file locations, and one can launch the automated downloads, this verification of the size and checksums. What about the large data sets? So example on the left, it's one of the simulated data sets, again, by the CMS experiment, about 10 terabytes, consisting of 30,000 files. So this will take quite a long time to download. So what one can do is to use the download file locations. And for example, there are, you can see on the right-hand side, there are many filtering capabilities. One can download specific file numbers or file names or even types. So there is, it's again, a one-liner to download one file from a given dataset for inspection, looking at the content. In addition to supporting HTTP protocol, CERN open data assets are all hosted on the EOS in the same manner as the experimental physics datasets are. So we are offering X-RUD access. So general public can access files over HTTP, but more specialized data scientists, theoretical physicists working with root directly can get the locations of the root files and access them via X-RUD, basically streaming on demand. Which brings me to the third letter of the FIR principle is the interoperability, which means that data should be ideally using vocabularies, should be linking to other data, and should be interoperable for other applications and workflows for analysis and processing. So here on the left-hand side, it's an example of the various data formats we are holding on the portal. Most of the data is exposed as root, which is the community standard experimental particle physics. But you can see, for example, there is some HDA, HDF, H5 data for machine learning, or JSON or CSV for simplified data sets. So there is also mini AOD, SIM nano AOD, which is basically reduced versions of the level 3 data available. But basically it all boils down, most of the data is available as root. And the metadata itself is described using the custom JSON shown before. There are no formal vocabularies used, but there is some common classification work. For example, we've been working with Atlas and CMS to establish a list of categories which might be good to classify the simulated data sets into. From the data semantics point of view, so how can one understand the data? This is an example of a machine learning related data set. On the left-hand side, you can see the description. There are linking to related data sets, to the parent data sets. And on the right-hand side, it's an example of the description of what the data set contains. So as much as possible, we are trying to come up with a detailed semantics description. Every variable in the data file is coming with its own types, float, integers, Boolean, strings, and a short description, so that we can ensure the understandability or interoperability of the data. And last but not least, data is coming with an examples, because this is the best to ensure that data can be understood and used. So there are examples of the analysis, maybe of the order of a dozen, 2 dozens, which are on the left-hand side. It's a Daimion spectrum in C++ and Python, and IPython notebook as well. And on the right-hand side, an example of a Higgs to Tau Tau analyzing the data we have released. And these examples are actually runnable. Recipes are provided on the portal, and Higgs to Tau Tau simplified analysis can be run within reasonable time using the given data. So this is how we try to ensure the interoperability, and the rerunning of the analysis brings me to the fourth letter, R, standing for reusable, which is the ultimate goal of the data preservation. So data preserving is open, having a very rich metadata should be done so that it is easier to reuse the data later on in light of new theories. So data should be basically coming with accurate, relevant attributes, clear data usage license. So in the case of data from the LHC experiments, it's typically CC0 waiver, fully public. Data should be coming with detailed provenance, information how it was basically born, how it could be reproduced, and meet community standards. So example of a data provenance. Simulated data set by the CMS experiment. On the left-hand side, you can see all the data steps, how the Monte Carlo was generated, starting from LHC, SIM, HLT, RICO, all the way through the generation simulation chain up to the format which is available and suitable for particle physics data analysis. So we aim at capturing the full data generation step provenance with the information about computing environments, for example, which CMS software release was used for this particular step. also all the configuration files necessary to rerun the process, and as well as any scripts which are used to run this. So most of the data records on the portal are coming with the full provenance information, which is also available in the custom JSON metadata standard we are publishing. This is an example of a methodology, how the data came to be, which is consisting on several steps. So first step is the SIM process. You can see the ID of the configuration file. And basically, CERN Open Data Portal tries to standardize the experiment information about data provenance in one common format so that the information about how the data was born could be understood up to the level of parameters. So which brings a question, could we actually reprocess some of the data we have released on the portal? So Eckhart mentioned that raw data is too...
You can't just wake up, you're not going to do it. Or rather,
yeah,
it's not a good incentive.
That raw data is not an essential focus on the portal because it's too complex, but there are some raw data samples published on the portal. So we can look whether we could actually reproduce some of the steps in order to validate our data provenance. And this is what we have done. So in order to reproduce the steps, one would need to start them in the environment where the data was generated originally. So we are taking advantage of the advancements in the container technology in the IT industry. So both Atlas collaboration, CMS collaboration, and the other LHCb Alice are publishing containers to encapsulate computing environment. So we are taking some of the CMS software framework containers for the given versions published by the CMS collaboration. We have looked at the computational recipes. So can we actually reproduce all the steps as we have detected them from the data provenance, create specific paths, read the condition data and run the steps. And we have looked whether we could actually rerun some of the data sets which were published. Which brings me to the 4 pillars of reusable computational research, because now we know where the data are. We know all the input files, data files, parameters. It's the CERN Open Data Portal who hosts them. The analysis code, it's basically the snippets identified by the provenance with the software frameworks. We know the computing environment. It's our Docker container with database calls to access condition data. And our computational recipes have been also identified. Shell commands, but in theory could be Jupyter Notebook or any computational workflows, declarative systems. And we would like to basically instantiate such an analysis and rerun it. Which brings me to the sister project called RIANA, which stands for Reusable Analysis, which I'm also leading. The idea is to install and run all the containerized workflows on various platforms, notably Kubernetes clouds, but also HD Condor for high throughput computing or Slarm for high performance computing. So the analysis is described by a series of YAML files. There are some examples for the CMS Open Data analysis, and the physicist can actually use command line client or web interface to submit such an analysis for computation to the RIANA cluster, which then basically schedules the job, runs the jobs on the workers among themselves for intermediate data use shared storage and take advantage of the image registries of the containers prepared by the experiments in order to process all the workflow and get to the results. And this is what well, there are 2 examples. We could try, for example, data analysis. So Atlas experiment example on the left showed some search reinterpretations as part of the searches, reinterpretation or recasting strategies. So Atlas 3 search groups are actually mandating now the workflow preservation as part of the analysis approval so that the data could be basically reinterpreted more easily later. So such a workflow is running on RIANA. An example on the right, CMS jet energy calibration. We are trying to look whether we could run some automatized workflows. And applying the same principles on the reprocessing of the CMS datasets. So it basically works. We have published maybe JET dataset from 2011. So can we actually, by reading the provenance, instantiate this kind of Rihanna YAML? Can we generate the workflow, which is basically the workflow factory takes care of generating the Rihanna YAML, which is then sent to the Rihanna platform for execution, reading the files from open data, and coming to the histograms. And then we can compare by the raw samples whether we are getting similar data which were released to the physics. Basically, the aim is to validate what was released. This was a work done by the CMS experiment together with us, and came to the good agreement, basically making sure that what is released to theoretical physicists is basically good and reproducible. So now I would like to open another chapter. See, CERN Open Data is not alone. So what is its role in the ecosystem of sister data repositories? One of which is the HEB data we mentioned, started from Durham more than 30 years ago. So around the idea of providing publication level data behind plots and figures. One of the recent advancements is that HEB data has been opening up to host more data types, such as likelihoods, which was a great achievement. Atlas Collaboration starts to publish likelihoods, and there are papers using the likelihoods already. So HEB data is widening the scope. You might know Zenodo, which is a data repository for long tail of sciences and very easy to preserve research software in. So if you have a code on GitHub and you establish a connection between Zenodo and GitHub via OAuth, every time a new release is being pushed onto GitHub by means of a tag, triggers a workflow where Zenodo downloads a copy of the data, mints a DOI that can later be used to cite. So Zenodo is now having more than 100,000 code software packages preserved as a DOI. But for example, you may not know that there is a machine learning community growing on Zenodo. I was mentioning the data science community publishing data on the CERN Open Data Portal, example on the left-hand side. But on the right-hand side, there is a machine learning data sets on Zenodo which are smaller in size. The typical distinction is Zenodo is having a restriction on how much gigabytes you can submit, while on the Open Data Portal, we are focusing more on the event level physics. So there could be hundreds of gigabytes that Zenodo cannot mention. So one more sister data repository is the CERN analysis preservation. We have heard about the certain embargo period before the data is open to public. So we are trying to apply the same principles because open science can be used in theory, fair principles, not only for open science, but for science which is naturally closed. So while the experiment is ready to publicize the data after verification for the Open Data Portal, the CERN Analysis Preservation Framework is a sister service which tries to capture data and all the knowledge associated with an analysis by means of a web interface and again, command line tools. So data together with the code and anything that is necessary to understand the data. So in our little family of digital repositories, if we print on the x-axis repositories for experimental collaboration on one extreme, and on the other extreme, repositories for individual researchers, and on the y-axis, event level data versus publication level data, we see a certain movement. So let's say HEB data started as a publication level data for experimental collaborations, but with the addition of more complicated objects like likelihoods, it's moving towards y-axis down below a bit. On the open data, which was born for experimental collaboration, event level data, we are now having more and more individual data science or machine learning driven data sets being submitted, as well as on Zenodo, which was born for individual researchers, is now having a communities of data. So all the various data repositories are collaborating together through the same Invenio digital library technology framework. And in the ideal future, one could imagine that data preservation starts early at the born of the data sets, and then some of the data published, captured in the analysis preservation framework could be opened for publishing in HEPData, pushed to open data, and interoperated amongst each other. We'll see how the evolution of the repositories and the content grows. Which brings me to the conclusion slides. So basically, I was trying to present what we are doing from the technology point of view in CERN IT department, together in close collaboration with particle physicists and the Scientific Information Service, to foster fair science by the means of a CERN Open Data Service, which is accessible to anybody, CERN Analysis Preservation, restricted to only the collaborations, and RIANA Reusable Analysis Platform, which is also available to everybody. The aim is to capture and share actionable data and knowledge behind particle physics data analysis without verifying that the examples work, the data provenance works. We cannot be sure that data will be understandable in the future. And the list below lists some of the contact persons we have been in touch with across the past years in order to make this happen. So everything we do is free and open source. On the left-hand side, you can see a screenshot of the CERN Open Data Organization on GitHub. But one of the best ways to get in touch with us is the new CERN Open Data User Forum, which we started last year together with the experiments. So there is not too many posts yet because it's young, but it's a perfect occasion to actually get feedback from you. So if you look at the data and there is something that does not work from the infrastructure point of view, or you would need more assistance to understand some of the physics behind the data, I would encourage you to send all the suggestions to the portal. We would be very happy to talk there. And if I had to summarize the main message of my talk in one sentence, it would be basically that opening data is not enough. We have more than 2 petabytes now of research level LHC physics data, which enables independent theoretical research. And there are concrete examples of this. But without runnable examples, data might be very hard to make sense of. So in the data preservation world, there is a saying that workflow is the new data. And this is what we are aiming at, to preserve data together with code, together with compute environments, and the computational workflow recipes to foster data reusability. So we have published an opinion piece in Nature Physics, which basically expands upon these ideas. And I have maybe 1 more minute, so I would like to show you a few glimpses on the future plans. So following the adoption of the common statement on the open data policy by CERN laboratory management and the Atlas Ali CMS LHCb totem experiments, which we have heard from by Eckhard Elsen, who was one of the basically leading power in the new open data policy, we are expecting a large increase in open data publishing in the coming years. So we have to get ready on the technology side. What we are thinking about is to prepare flexible hot, cold disk/tape storage solutions in order to make it cost effective. Maybe part of the data sets could live on disk, part available on tapes and available on request only. We are trying to simplify the ingestion and exposure of data sets by integrating more closely with the tools that experiments are using, such as Rusio or Direct, and basically automatizing even more testing and usage examples so that we can offer the best service possible. Thank you for your attention.
No, thank you very much for this really impressive overview of what's already been done at CERN towards open data. I enjoyed it very much. Again, I want to ask the audience and also the panelists if there is a question at the moment that's urgent, so Tibor can handle it right now. I don't see any hand. So we can always, I mean, this is, I think, especially the last point, that there is a forum that exists, that's something that we should not forget, that must be discussed further, because this is indeed the right crowd to start feeding you with some feedback that you might need for further developments. So this is something we should pick up later in the discussion. So, but let me now thank you again, Tibor, for your very nice overview and presentation on open data. And let me call the next speaker of the session, which is Philip Harris from MIT. Philip is also the research coordinator for physics experiments at the Institute for Artificial Intelligence and Fundamental Interactions, which is also called I-FI, if I pronounce this correctly. And yeah, Philip, the floor is yours.
Yeah, so thanks for pronouncing I-FI correctly. You're the first person not in I-FI who I've heard pronounce it correctly. So yeah, I'm going to talk about anomalies in the open data. And certainly we haven't found anomalies in the open data that I know of. So I'm going to talk about, let's say, a recent exercise, which was not with open data, but pretty close to open data. This is the LHC Olympics 2020. So I'm going to talk about this. And I have my own experiences with the open data. In fact, I use it to teach a class I have. So I'm just going to talk a little bit as well about my experience. But Tibor actually gave a very kind of thorough summary of what's going on. So I'm just going to augment his talk. Okay, so the LHC Olympics was in 2020, and there were actually two Olympics. There was a Summer Olympics and a Winter Olympics. The Winter Olympics, basically we looked at some of the data, and in the Summer Olympics, we looked at kind of all of the data, basically the released various data. So what actually is the Olympics? So the idea here is to make a bunch of pseudo data samples, and these pseudo data are going to emulate what it looks like in real collider data. In this case, a specific topology was chosen. And the strategy here was to release actually multiple pseudo data with various different hidden signals. So the idea and the strategy then was to have the community find the hidden signal. So see if you could actually find a signal in the data without actually knowing what's in there. So the idea here was to really emulate a realistic analysis chain. And also there was an emphasis to use deep learning to find the anomaly. So I'm going to review kind of the strategies that people did, and I'll talk a little bit about the formatting as well, since we are in the open data session. So what actually was in the Olympics data set? There were 3 black boxes. So black box 1 is to, we hit a Z prime, a heavy Z prime was hidden. Black box, and then Z prime decayed to 2 heavy resonances, so some X and Y. Black box 2 had nothing, and black box 3 was actually a hidden resonance with some mass 4 TeV that decayed to another resonance with another heavy mass. So this gives you actually a 3-jet topology, so 3 gluons. And as a function of having a heavy resonance decay to another resonance, you also have that it can decay to quarks. So you actually have 2 resonances here. So these are the 3 different black boxes. And it's important to note all of these actually were decaying hadronically. So the focus here was on using jet data sets to actually see if you could find these signals. In addition to the samples, the black boxes, there was simulations released. And so the simulations included a signal that was quite like the signal in black box 1. So instead of a Z prime, it was a W prime. The mass parameters of the W prime and the decays were different. So you couldn't just out of the box go from the simulation to the first black box. And in addition, a simulation sample was released, and the simulation sample had different Pythia parameters than the black box. And so you couldn't just, use the simulation as truth or do a direct comparison, right? So here's just a plot of the dijet mass, right, between the simulation and this is black box 1, right? So you can see there's some differences. You can actually go into the jets, look at the substructure, and actually the parameters are quite different. There's features in the black box data that are not present in the simulation. So this was, to say, a good baseline for analysis. And since we just had a talk on kind of presentation of the data, I wanted to discuss how the data was formatted. So in this case, it was a kind of machine learning ready data format. So it was an H5 file. So that you can load quickly with Python packages. And actually the data format was pandas based. So it's, if you do any machine learning, this is kind of the standards these days. And it was done relatively simply. So what was given was just an array, 2,100 entries long, and it was sorted by particles. So let's say the first 3 entries were a 3 vector for the particle, particle 1, and then the next 3 vector for particle 2, and so on. It was 3 vectors. The mass was excluded. We just had to treat them as mass 0, which is often the case. What we do with if you're dealing with particle flow. These are Delphi samples, so they're kind of a mock simulation of the LHC. So the kind of resolutions and the behaviors is quite similar to what dealing with actual data. And this was enough format to really start processing the data and actually doing analysis. And there were a number of scripts released so that you could see how to go from here to analysis. Since we're discussing open data, I want to just make a brief aside about open data. So one thing I should say is that with the LHC Olympics, I was a user. I wasn't one of the, let's say, creators of the Olympics. So I'm really giving this from a user's perspective. And with the open data, I'm also a user. I'm not, let's say, helping and derive things, but I have been involved in actually a number of open data analyses. So these. You may be aware of these somewhat controversial papers from Matthias Schott. So in fact, what you may not know is that to get these analyses out, he actually used an analysis framework I wrote. And so I'll explain a little bit about analysis frameworks and how he was able to get to these analyses quickly. Incidentally, I actually used the open data in my class. So I just taught a class where we did open data analysis of LIGO, LHC, actually a few other places where you can get open data. So I'm a big proponent of open data, but there are a few things to keep in mind. So just to contrast kind of the Olympics, the LHC Olympics workflow with a kind of minimum workflow you would need to do the same thing. Well, in the Olympics, you take this particle data set. So then you have to cluster the particles to make jets. Then you have to take the jets and compute features like jet substructure features. And then you can actually look for your anomalies. With the actual data, there's a few more steps. So in addition to clustering the particles, you need to do some sort of trigger selection. So the Olympics kind of tried to emulate this, but it's not the same. And in addition, right, you need to make a sample that's actually pure, let's say QCD, right? We're just released a sample that had pure QCD, but in principle, to do this in reality, you have to do things like lepton vetoes, right, to make your sample realistic. So the differences are not too large, but so the LHC Olympics was actually pretty good at kind of emulating things. In reality, though, to really do this in open data, or to really do this now with, let's say, open data, I think the real minimum workflow these days would have a few more steps. So currently what we do in CMS is, in addition to reading it, triggering it, you have to run some sort of pilot mitigation. So we run puppy before we actually cluster the particles. And in addition, once we have our jets, we run jet energy corrections, right? So you can actually match your data and simulation. And this is kind of the minimum standard you would need to really start to actually look at the data and actually compare it with simulation. And the way we typically do this, and the way, let's say, for example, Matthias did this when he did his open data, is he used an analysis framework that actually did kind of a standard pre-processing. And so the standard pre-processing usually involves running your pilot mitigation, going algorithm, let's say going and clustering your particles, making jets. Sometimes it will also involve applying the jet energy corrections, and even sometimes, let's say, lepton veto. So you can imagine kind of making this a little bit larger. Inside collaborations, there are many analysis frameworks. So I would say in CMS, there are probably about 10 main analysis frameworks that people use. And these are developed by groups. They eventually become, so like these analysis efforts tend to become centralized over time. So they get kind of like what we learn from these frameworks get merged into things like in CMS, we have mini AOD and nano AOD. But typically speaking, analysis developments start at the framework. So once you have an analysis framework, they're usually designed so you can go pretty quickly and reanalyze your data. So to run an analysis framework, it can take a week to run on a large data set. Whereas to do a specific processing, it will take, let's say, you try to aim for an hour, right, or less. And so typically on top of analysis framework, we usually have some scripts to go to a flat-end tuple, 10, 20 variables, the variables you actually use for your analysis, right? And so with Matthias, actually, we ran the analysis framework centrally on the open data samples. So we used my analysis framework I developed, and then I gave him some scripts to actually go all the way to analysis. So he had, let's say, a head start in the sense that by talking to me, he was able to get very quickly to being able to do analysis. A thing I should say is that frameworks take a long time to build, right? To actually get all of these steps to really work well and not have bugs, it takes many years. You kind of have to like build your framework and then fine tune it over time. And there's kind of a lot of institutional knowledge that's built up. And this kind of thing is hard to bring to open data. And it's kind of a question that I ask, to everybody. I mean, Tibor's talk was actually illuminating in the sense that, he says this is really where the developments are for open data. It's about bringing this knowledge into the open data. Once you have it, though, it's relatively easy to kind of go and start to do analysis. So here's a glimpse just of my framework, the framework we use for the open data. And just the other thing I should say is that when working with Matthias, he would often run his analysis, and then he'd have a bunch of questions about how the data is behaving. And so things like trigger preparation, detector issues, this information is also not in the open data, right? But the collaborations have heavily analyzed these data, and there's often kind of hidden knowledge that you need to know. So I strongly encourage people to look at open data, but if you're really concerned about the data, I think at the moment you still should talk to somebody inside that collaboration to make sure you're just not missing something that's obvious. Okay, so I'll skip this, but just suffice it to say that making data fair and making data easy to use machine learning readables such as H5 is starting to happen in the LHC, and you can go to Tibor's talk. So with that aside done, and with some idea now of how we want to actually analyze the data with the LHC Olympics, I want to actually go and show you what people have done. So the Olympics had about, in the end, about 20 different, or maybe 15 entries, and everybody did kind of different things. And so I'd like to show kind of diversity of approaches and see who discovered something and who didn't. So generally speaking, with anomaly detection in the LHC, there's kind of two schemes that people have focused on. And so one scheme is to kind of leverage one region against another. So you might be familiar with the classification without labels idea. So let's say you have a region in your data that could be signal free, and then a very similar region that has some signal, and you want to weigh one against the other. You can start playing these regions in data to see if there's something different. So this is what we typically call weak supervising. The other approach to find anomalies is to just look in the data for anomalies and build some sort of scheme or a set of priors for how you actually want to look at the data and potentially see if there's an anomaly. And this is typically done with autoencoders, so for anomaly detection. All right, so here's the results of the LHC Olympics, and I'm going to intersperse some of the deep learning concepts used as we go along, so that it makes sense. As a note, right, the black box one was a heavy resonance, and it decayed to 2 hadronically decaying resonances. And these are, let's say, light enough that you could actually reconstruct these as single jets. And so this is really a dijet scenario. And every, let's say, entry to the LHC Olympics kind of focused on this dijet topology. So they reconstructed jets. They computed either features of the jets or took the particles from the jets and fed this into their anomaly detection algorithm. I'm not really going to talk about the results in black box 2 or 3, mostly because black box 3, well, nobody actually found the signal. Nobody actually thought to look at a trijet topology. And black box 2 had nothing, which was quite depressing, especially for me as an analyzer. Like, my group thought we thought we had something, but there was nothing. But I'll talk about that a little bit at the end. So a lot of the entries kind of focused on the idea of autoencoders. So autoencoders are just neural networks where you send in a vector of inputs and you try to reproduce the same vector of outputs. And between the two input and output, you make a condensed space, right? Some sort of bottleneck layer where you try to kind of compress and just contain the features of data or of information in your data set. So this we often refer to as the latent space. And so here's the latent space for actually an autoencoder that can reproduce digits. This is a two-dimensional latent space. This can be arbitrary dimension. And you can see, let's say, some regions you'll have the digit 0, some regions you'll have the digit 7, digit 9, and so on. A thing about the latent space is it's a mysterious place, and things can appear and, let's say, 2 weeks later, just randomly disappear in your latent space. It's a bit of a mystery. And these are things we're trying to understand, but it's taking time. So the other thing that's, let's say, kind of happened over the past few years with machine learning at the LHC is people have gotten more sophisticated with the way they deal with their inputs. This is often referred to as your machine learning encoder. And so if you look at kind of the history of JET-based machine learning, about 5 years ago, people were still looking at convolutional neural networks and trying to send images to classify their JETs. More recently, people have gone to sending the 4 vectors and kind of the features of, say, secondary vertices to your neural network. And this you can do with a recursive neural network, such as an LSTM. And more recently, people have been using encoding architectures that actually can take in the particles and their correlations, right? And so this you can do with a graph neural network. Current kind of collaboration results and kind of the public standard is this middle point. In addition, for autoencoder technology, there's been a similar evolution. So the traditional autoencoder just had kind of a latent space, but more recently, people have, instead of building a latent space, they build kind of 2 latent vectors, one vector for, let's say, a resolution, and one vector for our mean, and you actually sample Gaussian distributions from these vectors, and then you build your outputs. So there's some smearing involved. The idea is to make this strategy makes your latent space more contiguous. And this is called a variational autoencoder. And more recently, people have built, mostly building on the variational autoencoder design, to actually use transforms to get into a latent space where you can actually sample Gaussians. And so they build actually a functional transform that can change as you train your neural network. And then you invert this transform to get back your inputs. So this is called a normalizing flow. So it's a kind of extension of variational autoencoder. And you can combine your encoder, your latent space interpretation, whether you use a normalizing flow or just a vector, and then you can decode, right? So you can do all sorts of combinations. All right, so here's the first entry for the LHC Olympics. And this is a kind of a simple autoencoder using high-level features from the JET. And the strategy here is they used a GAN to kind of improve their autoencoder, and they used a bump hunter algorithm. This is a kind of standard algorithm to look for a bump on a distribution, and they didn't see anything. Their bump hunter algorithm did not pick the right excess, but actually, if you look at the data, they do have kind of a little bump here, which is actually right where the excess should be. So the conclusion from this is it's pretty hard to get the signal in the black box. You can't just kind of work out of do something simple. And, yeah, so that's the takeaway from that. So going a little bit more complicated, here's an algorithm that used a variational autoencoder. And this variational autoencoder was slightly modified. So one thing I should mention is that if you want to find a bump on a distribution, you want to make sure that your neural network is not correlated with the kind of extraction variable that you're working on. So this is the dijet mass. In this case, we're looking at dijet scenario. So everybody had kind of different strategies to decorrelate their algorithm against the mass. So this one, they put it into their decoder of their variational autoencoder. And then they cut on their discriminator, and you can see actually they got quite a nice bump. They didn't quote a significance, so there wasn't a signal extraction here. But you can see that this algorithm starts to seem like it works. So already we can see something in black box 1 pretty significant. So here's approach using normalizing flow, and they didn't see anything. And so the strategy here is, again, normalizing flow with some scheme for decorrelating the mass. And if you look, they don't see anything. My interpretation of this is actually that their algorithm might very well have worked, but they just cut too loose to actually see anything. All right, so here's an approach of an autoencoder. Now, instead of using high-level features, so the previous were just high-level features of the jet, here's one where you actually send the particle 4 vectors into your autoencoder, and you build a variational autoencoder that outputs, again, a collection of particles. And the strategy, and so they did this on their black boxes. And so if you look at black box 1, they see kind of a bump here. They didn't have a quota significance on this. They didn't quote a signal extraction strategy, but you could convince yourself this is pretty good and potentially comparable with this variational autoencoder approach. One thing that was noted when doing all of these different autoencoders and more generally is that kind of this training strategy is critical. So this variational autoencoder, they spent a lot of time actually getting a good convergence of their training. So this is something we learned from the LHC Olympics. And actually in this particle-based one, the preparation of the inputs was critical. So here's an approach now going all the way to a graph-based autoencoder. And you can see, again, they send in the particles, but they use a graph neural network on top of this. And they use the bump hunter algorithm. And now they actually see an excess where you expect it at 3.8 TeV. And so they were able to get 2 sigma axis. This is the first quoted significance. All right, so those are the kind of the anomaly detection autoencoder algorithms. Sorry. So now I want to talk a little bit about weak supervision. And so the strategy with weak supervision is to play one region, say sample A, against another region, sample B, and look for the differences between the two. So sample B has some anomaly. So if you, let's say, took all the flowers in A and trained them against the flowers in B and asked for a difference, well, eventually the red flower, the red tulip in this case, will come up. But practically speaking, with weak supervision, the problems are usually a little more difficult. You don't have a pure sample where you have one anomalous signal and then a pure sample with nothing. You typically have mixtures. So you want to train a sample that has, to say, a larger admixture of your signal and a smaller admixture of your signal. You train one against the other. So that's broadly speaking the strategy. There's various different ways to actually approach this problem. So kind of the simplest approach is to do topic modeling or clustering. And so the idea here is, well, it's simply speaking, if you have a distribution and you want to kind of separate the distribution into its features, you can imagine, let's say, one end of the distribution, there's one end of the distribution will have, let's say, a lot of from one sample, and one end of the other distribution will be concentrated with a lot from another sample. And if you have, let's say, for example, multiple distributions, right, where the various samples A and B are varying, you can actually then solve a system of equations and actually extract out the various different subsamples. This is so-called topic modeling. So you extract the topics. Equivalent approach, or almost equivalent, is a clustering algorithm. So you can imagine going to the latent space and clustering it. So a more sophisticated approach along the same lines is now with arbitrary dimension. You can just take sample A and sample B and train a neural network. So train a classifier between the two. This is the classification without labels, or Koala's hunting algorithm. And then a more sophisticated approach is actually to construct a likelihood of one sample and a likelihood of the other sample. And you can actually do this through a normalizing flow. So you can actually compute a probability distribution of your event to be within sample A or B. And then you can just compute the likelihood ratio between these two, actually see which regions of A and B are most discriminant. So here's an approach in the LHC Olympics using topic modeling. So this approach, the idea was just to build a 2D distribution of the jet mass and look for a signal. And with the kind of R&D data set, they're able to extract signals. So in this case, they look for 3 different subsignals in the jet mass, the first resonance, the second resonance, and the background. And you can see they can, modulo some wiggles, they can actually extract this. This is for a signal that's 1% injected into your background. It turns out if you go down to 0.1%, which is where the signals were for the actual black boxes, this method starts to break down. So that's what we saw there with topic modeling. You can imagine a more sophisticated version of topic modeling. So there's an algorithm called latent Dirichlet allocation. And instead of just taking, let's say, one distribution, this uses a jet splitting information per jet from declustering your jet. And then with the LDA algorithm, you can construct a probability distribution within the samples, and it will try to kind of maximize the distance between distributions if you tell it to split your sample into multiple distributions. And then you can construct a likelihood, right? So what's the probability that your distribution or your set of distributions has, let's say, one feature versus another feature after you've done the splitting with the LDA algorithm. And with this approach, they didn't see anything. They didn't see the black boxes. But certainly, this is a very powerful algorithm. And the kind of conclusion is that maybe we just didn't give it enough information. All right, so then a last approach, or not a last, another similar approach, like topic modeling, is to actually cluster. And so the strategy here is to cluster in the latent space. So you construct a latent space. This is actually a latent space from a supervised network. And you can cluster in it. So in this case, we took 2 clusters to look for anomalous region and non-anomalous region. And in the R&D data set, they were able to extract a signal. However, there was no signal when they actually looked in black box 1. And again, this is another approach that kind of breaks down when you have really small signals hidden in. And now we have the Koala approach. And so the Koala approach, the idea is to just train a normal, let's say, MLP classifier network. This again used high-level features. And the strategy here is to just scan the mass. So you build sidebands, right, where you have your signal-free region, and then you have a signal region, and you try to train your signal against the sidebands. And with this approach, we're able to get a 5 sigma excess, right, in black box 1. So first, very significant bump from the hidden data. So this worked quite well. A note is that if you actually try to use the Koala paper, it won't necessarily work because to get this to work, actually, they need to make the jet masses dimensionless, right, as an input. So they send the jet masses, but they actually divide by the dijet mass. So here's another approach. This approach was kind of a shocker to all of us, because this actually came from astrophysicists. They presented this at the Winter Olympics. And this is probably the most kind of convincing discovery in black box 1, at least in the Winter Olympics. And the strategy here is actually, again, the Koala strategy, but using normalizing flows to construct a likelihood of your events as a function of mass. So you train this on the data, and you can compute a likelihood that your signal is at some sideband region, let's say region B, versus a signal region, right, region A, within a mass window. And they have a sliding mass window you can scan. And so you can see, if you see that there's a kind of a discrepancy where there's events that are very likely to be in the signal region, but not likely to be in the sideband. And you could cut on these events, and you see a clear access very much consistent with the actual black box 1, which was a 3.8 TeV. One note, they didn't quote a significance, which is a little sad. They didn't have a background strategy. But you can see this is very powerful. So now another kind of related approach was to kind of play autoencoders against the Koala strategy. And so the idea here is to use an autoencoder to kind of split the data into 2. And what you do is you actually use the dijet topology. So you train an autoencoder on one jet, and then you actually use the Koala approach on the other jet. So the autoencoder on the one jet, you can kind of separate the one jet into anomaly-like and not anomaly-like. And then you have 2 samples, which you can then run the Koala algorithm. So you can actually train a classifier to separate the anomaly-like versus the non-anomaly-like. And so what you can do is you can do this with one jet, do it on the other, right? And conversely, do it on one jet, run the autoencoder on the other jet, and then train the Koala on the other. And you can do this iteratively and kind of improve your classification between anomaly and non-anomaly. And this worked on the black box data set. They found a 4 sigma resonance. And as a note, they thought mass decorrelation would have helped. So a last development is to actually try to blur the line between kind of conventional supervised training and autoencoders. And so the idea here is, if you have an autoencoder, you kind of construct a latent space that captures the features of your data. But then if you have some data where you can actually label it, you feed that into the autoencoder and you actually try to label your latent space. So if you know, let's say, for example, this latent space has red tulips and purple tulips. Well, if you get a tulip that's not in here, so for example, a very dark purple tulip, which is not in this image, it will try and put this tulip near the other tulips in the latent space, potentially near the purple tulips. If you had a really true anomaly feature, like a sunflower, it wouldn't fit in your latent space nicely. It would be far away from everything. And so this is a nice way because you can actually kind of classify excesses that are signal-like versus a detector glitch, which would be far away. And kind of the strategies to do this are to just do a supervised training, but use incorrect signals, just to hope your signal is similar. A more sophisticated approach is to actually build this on top of an autoencoder, so you can use the latent space for your supervised training. And then another approach is to actually use autoencoders and can kind of train this on incorrect signals and train this on background, and then build a space out of this where you can search. So here's an approach just doing supervised training. And here they were able to get an excess in a similar region, but it's not a convincing signal. And so now I want to talk about the last approach, which was my entry into the Olympics, which we call quasi-anomalous knowledge, or QAC. And the idea here is exactly what I was saying before, is to actually train two autoencoders, one on incorrect signal and one on background. And you can then construct a space. So on the y-axis here, we have the loss from your incorrect signal. On the x-axis, you have your loss from the background. And so anomalous features will have a large loss. They won't fit with either the signal or the background. So this could be a detector glitch. A signal that's, let's say, close to your hypothetical signal will have small signal loss and large background loss. And, let's say your true signal, if it's similar, they'll both be in this space. And so you just probe this space. And certainly you can add libraries of signals and make this an n-dimensional space. In this case, we used normalizing flow autoencoders for this. And just as a note, we were able to actually kind of exceed or get as close to supervised training with this approach. So in fact, if you know the signal, you can actually make an algorithm that's just as good as a supervised learning. And more robustly, right, if you take this algorithm, right, train it and compare it to a supervised algorithm where you vary the samples. So this is the same. So the dashed lines here are supervised training, trained on this red sample. So that background against this signal. But when you apply it to another signal that's far away, the performance goes down. If you apply it to a signal even further away, the performance goes down. But if you use QAC, the performance actually stays to be robust, no matter what your signal sample, as long as your signal sample is not so far away. But it allows for things to be robust because effectively you're making a continuous space you can probe. So we did this and we made our QAC space, and then we just did a bin fit where we actually do a mass fit in bin categories. And from this, we were able to get 6.3 sigma significance. So you see a clear bump right at where the black box lives, and it's pretty convincing, and we got a large significance. So that kind of gives you an overview of what we saw at the LHC Olympics. There were lots of interesting discussions about how we could train on the data, in this case, train on your black box sample, and not train on it, how to use a simulation. This is an open discussion. I don't think we've concluded. Here's a just fun look at the results. I'll let you guys look at this offline, but you can see they're fun things like a human neural network that had results. And what you could see is, at least this is at the Winter Olympics. At the time of the Winter Olympics, this GIS method, which is a normalizing flows with the Koala approach, was, say, the only one that was really able to capture all of the features. And nobody found anything in black box 3. Black box 2, here are the signals. So here's the QAC approach. I was like, my students and I were really convinced we found something, but we didn't see anything more than 3 sigma. It's like 2 sigma-ish. And that's kind of a point about this, is that you will see fluctuations in your data. And the fact that nobody else saw anything was kind of a hint that maybe we weren't doing things right. So observations of this approach, the conclusion that I have from this is that really a diversity of approaches helps. We don't know what our signal is, and we need to have, like, throw all of the ideas against the table to really help. Even for then, nobody was able to find anything in black box 3. So everybody had kind of this implicit bias to look for resonant digits. So we actually in some sense failed. This kind of brings us forward to, kind of ways we could compare strategies together. So one thing that we haven't solved is that, in terms of comparing sensitivities, we just picked a bunch of models. It's not clear that this is the most robust way to contrast different methods. So in terms of comparing the observations, I don't know if I have enough time, but one thing that we did observe, so there was a study actually to contrast the autoencoder approach with the Qualo approach. And what you see is that actually, if you vary your signal purity, the autoencoder approach will be kind of the best, whereas the Qualo, the weak supervising approach, will get much better once the signal gets large enough. We saw that semi-supervised methods actually push things further because you're kind of injecting signals to reduce the space of autoencoder. And that actually would make your sensitivity even further. And you could speculate that a curve, something like this, and you could further speculate that adding the weak supervision on top of semi-supervision might really get you ability to make real discoveries quickly. But this is all kind of open research. There's a lot we learned from this. I thought that dataset was a great tool. It's very tractable. It's quite simple. It was easy to use. And I think it's the kind of thing that we can even think about doing fun things like merging strategies and exploring. So in summary, if you're dealing with open data, there's always a little bit of black magic that goes in. You really should talk to somebody in the experiment to really understand the finer features of the data. And in terms of the LHC Olympics, from this exercise, it was a nice community effort. We saw a broad range of anomaly detection algorithms. And it's clear after, being part of this, it's not just one method that's going to help a discovery. It's really a diversity of approaches. All right, so thanks to organizer for inviting me. Let me know if you have questions. Thank you.
Thank you, Phil. That's a very nice overview on a practical approach to open data by the LHC Olympics. Now, before we come to the questions, I want to ask Nishita Desai from the Tata Institute of Fundamental Research to take over. She's going to be the discussion leader of this session. And Nishita, the floor is yours. And if there are questions to any of the speakers from the session, refer to her and the speakers. Thanks.
Thank you, Oliver. Yeah, so Philip, if you could stop sharing, I'd just like to put something on the screen. So what I tried to do here is just to condense what we had in the talks today in just one slide. And to begin with, I'd like to start with any questions we have for the speaker. So one of the things that I thought was important and was stressed in the very first talk was that it's not enough just to release data, but also algorithms to be able to process the data and extensive documentation so that people can understand how to use it. And one important thing that was pointed out both by Eckhart and by Philip is that a lot of knowledge that is used to sanity check the data and the algorithms is actually known only to the collaborations themselves. And it's not yet clear how to make it open. And it was interesting to see, for example, Tibor showing us these detailed metadata in JSON format, which sort of attempts to make this more public. It was also nice to see, and very impressive to see multiple avenues for publication that are open. There's already a forum for discussion for open data. So that's, I think, also something that would be interesting to a lot of us. Yeah, the LHC Olympics was definitely an interesting take on how we can, if there is something, will we actually see it? It's always the question that we ask. So that was interesting to see. The answer is not always. And finally, a question from me to all the experimentalists and all the open data experts out there is how realistic is it that this framework can actually be used by theorists in some reasonable time frame? So this is just some talking points, but of course you're free to ask your own questions or have your own concerns. So do we have any questions? Okay, so I see a hand. Sorry. Yes, Tao, please go ahead.
Yes, thank you very much. Thanks for the speakers for the wonderful talks. I have been always an advocate for the open data practice. And in 2006, there was a very large SUSE conference in UC Irvine, and there was a panel. Discussion about this. And of course, I was on the panel to push for this open data, but didn't go very far. That was not ready. Now, I have a question. I really want to thank Eckhart for this very nice talk. I have a question for him. So, of course, we're talking about this, your level 3, the level 3 data. And but nevertheless, LHC has a huge amount of data. So we have to be very selective in any case. It's just impossible in terms of manpower, in terms of analysis, in terms of the need to have the all data analyzed if possible. So what would be the selection criterion that from your mind, do we eventually have to fall into the triggering categories, like you have a certain amount of data with large missing energy on the one hand, or another data sample with isolated leptons, B tagging and QCDJS. So what would be the standard for you to choose to select and to publicize the data? It's going to be very limited anyway.
No, it won't be limited. I think the idea is really to release all the data, but not immediately. So the philosophy, let's take Atlas and CMS. I think the intention is really to release the data, well, above a certain trigger threshold so that there is no ambiguity after some time. So run 2 has been recorded, well, the run ended in 2018. Take 5 years from then, so essentially the run 2 data will become available sometime in the second half of the 20s. Run 3 is another chunk of data, and give it, because it doubles, or will hopefully double the statistics of the previous runs, it will then also be released after some latency. And so the idea is really, in the end, and that was also my alluding to data preservation, in the end, all the data will be made available. It's quite different for LHCb. LHCb has decided for run 3 already to record the data in various streams. Let me simplify it to have a stream for charm data and some charm data, a subset of charm data, and for certain neutral bees, for example. In fact, if you look at what they are doing, they have many more channels. And depending on what the channel is, they will release that data accordingly. So the pressure from LHCb, in fact, to release the data, even though they have much less data than the general purpose experiments, is really to have many petabytes, let's say 10 petabytes, in contrast to the canonical 1 petabytes per year release. The point of not releasing immediately is, well, of course, they want to have the first peek and take the pride to find new physics first, at least for a certain amount of time, but also to make sure that they understood the calibration to much detail. And it's it's really a chore. If you take the Atlas experiment, who published, when was it, 4 years ago, a precision measurement of the W mass. To get to that level of understanding of the data, it takes an enormous amount. Yeah. And they're still far away from achieving that for run 2. So this effort really needs to be given some time. It has nothing to do with the collaboration not willing to do that. It's really just a tremendous effort. But where it's not needed, hard physics, I think the data will be released rather quickly.
Yeah, that would be very impressive. So my follow-up question would be, don't you put them into the different categories, the data according to some classifications, such as trigger features, and how can we put everything together in such a big data sample then?
Certainly for LHCb, but I see Kati is also offering to answer that question very specifically from the CMS point of view. Kati has been driving this open data effort in a very prominent way. So maybe Kati, it's best if you answer that directly.
Thanks. So this is Kati from CMS, taking care of the data preservation and open access. This is a good question. What we release is what we have. So the data, when data taking, they are driven to different streams, which are our primary data sets. And that's what we release. So we don't make any additional preparation for the data to become open data. We use them as we use them ourselves. And this also, it's important because then we can rely on the validation procedure which has been done on this data.
Okay, thanks. So that would be important to discuss and communicate with the community, and in particular theorists, for their need. Sometimes we theorists come up with new ideas that may not be properly triggered according to your trigger categories. And that would be nice to have such a large data sample available and in certain particular purposes. And I think it's important to continue for the discussions with the community. Thanks much.
Yeah, thanks, Tawe, Kurt, and Kati. Bruce, I think you had a question.
Yeah, so I have a question for Eckert and another for Philip. By the way, we really want to thank the three speakers because that really was an amazing overview of where we are today. And this is very important for our field. So, I mean, my first question, which is triggered by some of the materials in the first slides by Eckert. I mean, being in South Africa, we basically have two relatively large communities. We have CERN community, and then we have an even bigger community that is driven by the square kilometer array. I mean, Eckert knows, but for everybody else in the audience here, the SKA is basically the biggest wave astronomy experiment in the world, and it's becoming one. And South Africa hosts 2/3 of it, where the other 1/3 is hosted by Australia. So obviously the issue of authorship, number of people in the author list, and the sharing of data is very important to us. So we basically have the two communities talking to each other, and it's very clear that the issue of sharing data and openness is a cultural one. It's very clear because when you talk to one community, you get one point of view, and then when you talk to another, you get a very different point of view. So it's clear this culture has been generated over the years, or if not decades. So obviously, the downside of sharing data is that there will be some people that will rush to publish bumps, or which is easy, as we know, when you don't have a lot of data, as we have seen in the past. But obviously, these are the downsides that we have to manage as a community. So my question towards, which is addressed towards Eckert, is the fact that it's clear this is a cultural issue, and we need a cultural shift, not a cultural revolution, but a cultural shift where the theoretical and experimental communities find a different equilibrium that the open data provides as a way to bring the communication to a whole new level. So my question is, I saw this by Thibaut, this very interesting link to a workshop that was organized at Fermilab, I believe. I was wondering if CERN was planning to do something similar, so that this communication between theorists and experimentalists is brought to a different level, and gradually we get into a different kind of disposition when it comes to the open data. And I will let Eckert come in first, and I will ask the question to Philip.
Yeah, so just to say something about that, Bruce. So I actually attended the Fermilab workshop as a theorist. It was open data for theorists. And yeah, so I did attend it, though having a 12-hour time zone difference was not very conducive to being very intelligent in the workshop. But I think my first impression was definitely that it's extremely complicated for theorists to, first of all, even learn the vocabulary that is required to understand the data that's available and all the processes that go around it. So that's just my theorist's impression for now. So Kati, I think you also have a comment on this, on the CMS Open Data.
Yes, I can say a few words of the workshop that was organized by the CMS experiment together with LHC. Indeed, first of all, for practical things, yes, we are planning for the next workshop, very likely this July, on sort of a CERN afternoon time scale. And I think this the concept of your concept of this cultural approach at how people think about open data, I think it has changed a lot, because we have had people using the CMS Open Data, which has been out there for 5 years, very responsible. It's really we have had no problems of false claims, and people have used with the open data paradigm. So what they do, they keep it open. So I think that has been very, very supportive. And well, also as a side remark for the Nishita, yes, we really understand that it is complicated. It is complicated, and it is one of the goals of the workshop to build the common sort of common understanding from our side. How long is the bridge that we need?
If I may add to that, it doesn't come without work. In fact, for both sides, both for the experimenters who record the data and for those, I wouldn't only say theorists, there are also other people just wishing to look at the data. Because, I mean, take the example that I think is quite well known. The first observation of gravitational waves, once the paper was out, the data was also a part of that. In fact, the signal data was made available. And then there were concerns about the analysis method that was employed. And the collaboration, the LIGO collaboration, LIGO LHC rather, went to quite some work to discuss without criticism why, in fact, the analysis that had been carried out was solid and, in fact, was withstanding the concerns that were raised independently. So in the end, even though there was already a publication, the profoundness and the solidness of the data analysis became stronger because of that criticism. But of course, it cost a lot of work on both sides to carry out this discussion. I think this is one of the best examples how science actually gets better through openness. But it comes with work, of course. And likewise, you know, I think you mentioned the theoretician comes up with a bright theory and wants to test the theory. Yeah, it's not easy. It may take a master's thesis or even a PhD thesis to verify with the data, but it may be worth it. And it's still much less than the original effort of recording the data. So as Kati says, all effort should be made to make the data accessible. I want to emphasize again, there is even the much coarser resolution data, the old Durham database, HEP data, where you can get some N tuples and carry out some very simple analysis, but without suffering from original binning decisions that the authors have taken in the first place. So I guess you are arguing about something that is in between HEP data and the data that is released. And okay, maybe there should be an intermediate version, somewhat more aggregated to make it easier, but you will lose resolution if you do that, of course. So yeah, our field is complex. But Bruce, if I may make a comment still on the SKA and LHC, those communities also know a little bit. I'm quite fond of seeing collaboration extending, even in data crunching techniques between the SK and LHC. And I think that will lead to probably also sharing of methodologies and the ethics of looking at the data. It may take some time. Remember, also for the LHC data, it took 10 years or so until we got this point, and it's still fairly new.
Thanks, Eckert and Katie. And quickly, I've been listening to Philip's talk, and I think towards the end you say that only one technique was able to see all the signals, and I'm puzzled or intrigued as to why that is. Maybe Philip can, maybe it was just the authors of that one were more savvy, or is really fundamentally linked to the machine learning method that was chosen for.
Yeah, so let me be clear. There were a number of different groups who actually saw the excess. They saw an excess in the digest mass. At the time of the Winter LHC Olympics, so this is the first incantation, when the black box one was revealed, there were order 10 entries. And I would say 3 groups found an excess in digest mass. And then 2 were pretty convincingly clear. But only one group actually found kind of the other features in the data, right? The mass of the 2 resonances, the approximate number of events. And interestingly enough, the group that did that there was not a group of high energy physicists, it was a group of astrophysicists. And so they had actually developed an astrophysics technique and talked closely with the organizers. So they understood the data, and then they came and presented the result. Why it was an astrophysics group that did this, it's an interesting question. I don't think there's a real answer. I don't necessarily, think it's that they had better methods. It was maybe more they had a more open mind about this. But it's kind of an interesting it's kind of issue. Just about how this, like the LHC Olympics came out. I don't know what to say beyond the fact that it was interesting to see somebody from outside of the community make kind of the biggest, clearest discovery at the time. Other groups have subsequently found the same excesses in the data, and even explain the features. Other HEP groups, but the first one was really this astrophysics group.
Interesting, thank you.
Thanks. More questions for today's speakers? Okay, I don't see any hands. So I go to a question that was asked on Mattermost, and I was just asked to read it out loud because the person who's asking is not able to speak. So the question is from Jennifer Kyle, and it seems to be to the general community rather than to a particular speaker. And she says that she and Julian von Wimmersberg wrote a paper based on archived data from Aleph a few years ago, and they are interested in having their results confirmed or refuted by other LEP experiments. And to the best of their knowledge, the data sets of Delphi, L3, and Opal are not open. However, they are under the impression that the analysis chains have been preserved. So are there any prospects for opening data sets from other LEP experiments? I'm not sure if there's anybody in the audience today who can answer that question.
I can try maybe. Quite surprisingly, the Babar data are probably the next to enter the repository. This is simply because, well, bluntly, it became too expensive at Slack to maintain the data, and here it would fit into an environment that maybe allows it. The other much older data, which I'm sure you may have heard of in the context of the data preservation effort, is the old JADE data, that is 80s or so. But I mention that because many people from Jade went to Opal, so it could be, I think it's quite conceivable that the Opal data will enter that repository as well. The discussions are not as advanced as for Baba and for Jade, but it will take time until they enter. The collaborations are still intact. They are at a very small pace, even in producing publications from time to time. So I think we can expect that data to be preserved in this environment as well. But I'm not in a position to give you an exact timeline for that. But it's the intention, and it was part of the discussion in the Scientific Information Policy Board that took note of this achievement for the LHC data, and then encouraged other experiments to follow suit.
Thanks. More questions for the panelists? Okay, sounds like nothing for now. Right. So I would just like to leave with an open question for everybody: is what would be the next frontier for this field? So what exactly would be the very next thing that we look forward to? People are thinking. Yeah.
I mean, I just in the context of my talk, I was thinking in the context and this meeting, it might actually be interesting to do an LHC Olympics, but with real simulation, right? So so kind of actually use kind of actual collaboration simulation, and see if people could find make equivalent discovery. Certainly when you get to that level, it also makes sense to then look at the data afterwards. So you can imagine an exercise like that.
Yeah, absolutely. I think extending the LHC Olympics to use actual data rather than the toy data that was used is definitely a first step towards answering the question whether we can actually see something. And of course, since there is no big anomaly at the moment, we would have to rely on simulated data from the experiments. So that makes total sense. Yes, Eka, please.
Yeah, I think when we started this, there was a lot of concern from some experimentalists whether it's worth the effort. Basically, the short story was, well, we try to make the data available in a format that is digestible for the canonical theorist, and then there will be nobody to look at this. So it's all in vain. And remember, it's a big effort. And this was also the first comment that I heard in the CERN Council. Who will pay for that? We council delegates would say, we paid for the upgrade of the experiments, we pay our scientists. Why should we also now pay for somebody who has not contributed financially to this? And the short answer is, of course, you want every scientist to look at the data to get the best and squeeze out the last bit of science that is in there. But it's not an argument that goes easily. So what would be helpful if it could be shown that this effort in fact is useful, so that we see more PhD data coming out here, that we see more machine learning, quantum computing when they come along, efforts be based on this open data, and people see that in fact those people external to the closer LHC or whatever community actually drive the science as well. I think this was one of the best results. And if that can happen, I think Olympics may be a good solution, but I'm sure there are others in which this could happen.
Yeah, I think you bring up an important point that it's never conveyed that what has been published has been useful, and therefore the motivation to put in the effort and time to do it does not rise, essentially. So this is something we also face with the canonical theorist readable information that you mentioned. So we've been talking to experimentalists in what we call the reinterpretation forum to try and get out as much information as possible from the BSM analysis, mainly SUSY and exotics, so that we can reinterpret them in terms of whatever new physics models that we may have. And that already has been quite a struggle, because it's not a simple matter of just providing certain numbers and upper limits, but we find that as the analysis themselves get more and more complicated, it's not possible to unweight efficiencies in the way that we need them. Either things are too simple that you cannot apply them to new models, or things are too complicated that you cannot get that if you use those efficiencies, you don't actually satisfy closure tests, so you don't really get anywhere. So it's sort of a complicated balancing act, even when it comes to the much more simplified version of reinterpreting these analyses. So I'm sure it'll be much more complicated to actually use open data in a way that can be trusted and published. And I guess that also comes back to what you said in the beginning about who takes the blame if something goes wrong, which is also an important question, even though we did not answer that very much in this discussion. So more comments, questions for the panelists? Tibor, yes, please.
Yeah, maybe to your reflection, I can share one possible paradigm shifting with the more and more data being published. I mean, LHCb speaking about tens of petabytes, it might affect also the computing models, because it would not be reasonable for theorists to download all this data all around the world. So basically there is a paradigm of data going to code versus code going to data. So one could picture different computing models extracting something from the data by sending code where the data is, in order to basically make the process more effective. And this is something which is very similar in other communities like astronomy, where there are different data from different telescopes in different institutes, and doesn't make sense to move the data all the way across. So that's maybe one frontier to think of for the next years.
Thanks. That's interesting. I had not thought of that before. I think Ashutosh wants to make a comment. I think you're unmuted now.
Hi, it's Ashutosh Kotwal from Duke. Actually, just to follow up very briefly on a comment you just made, who takes responsibility when something goes wrong? We have a process for that, right? In science, which is you publish a follow-up paper, you explain exactly what was done before and what was discovered about it, and therefore a modification is done, and therefore a new answer is published, and so on. How is the issue of responsibility handled in astrophysics, cosmology, where public data have been available for a while? So they must have already answered this question of yours somehow. So I wonder if you can just learn from that, maybe see if you can emulate it.
Mm-hmm. Yeah, that.
Can I?
Yes, please.
Okay, so the answer is very quickly, because of the complete separation between those who build the instruments and who analyze. So if you have two analyzing team with a conflicting conclusion, then they have to carry the debate amongst themselves. Whereas for LHC, those who build the instruments and analyze are the same people, the same collaboration. And therefore, you can blame it on, well, these people don't don't understand the apparatus, or you can put it like that, or the analysis was naive or was started with too simple assumptions or whatever. And that's a fine borderline. And since the collaboration released the data, they are always well, you can put it like that. Why did they release the data in a way that is so confusing? And you can never escape that that blame.
If I may follow up, Eckhard, quickly. So in the Astro arena, this issue is handled, presumably there are also the building teams that have to make calibrations before they release. So then how do they handle that aspect of the responsibility?
Well, the simple version is if you take the satellites, they get a contract to deliver within specs, and they do that, and then their job is done. So it's almost like well, in some areas it is a commercial activity. They get the specification for a certain camera. They have to show that they fulfill this on all the channels, or they guarantee a certain low number of channels that they will never exceed, not to be functioning. So that is almost a formalized procedure, whereas for the analysis, they have to take it from there with the specification they get from the instrument. You don't have this fine interaction that exists in the LHC where, you know, an experimentalist is really challenged to squeeze out the last piece of information, even if there is a flaky bit. Probably in astronomy, you don't do that. You're not worrying about a failing channel, you just discard it. So here, that's the difference somehow.
Thank you, understood. So it's not quite as easy for us. It's not easy for them, but it's harder for us. Okay.
Yes, I think so.
Yeah.
I think Katerina has her hand up for a long time. So if someone can unmute her, please.
Yes, thank you. Wasn't too long of a time, thanks. So maybe a question in.
Did we lose Katerina? Okay, we wait for her to come back. So Kati, I think you have a comment to make.
Yes, just a comment on the responsibility. I think this is open data in a certain sense, well, in a very, very definite sense of it. And everything we release are released as any open data. We are released under Creative Commons waiver. So it is clearly stated that neither, for example, for CMS data or CERN endorses any works or produces during this data. So it's really always up to the people who use it. So in a similar way that we are not claiming PTA authors from our wrong results we get from it.
Right. But I was actually thinking more on the lines of what happened after Opera, for example. Even though they were very open with not understanding their result and so on, the media picked it up and it turned into a fiasco. And essentially, it fed into the mistrust of how science is done or what scientists are doing. So that I was thinking more on that sense. I mean, not in the sense that somebody publishes a wrong paper. That's not really the biggest problem that we have with misuse of data, I think. Yeah. Anyway, I think Katerina is back, so maybe you can ask your question.
I should be back, I hope. Can you hear me?
Yeah.
Yes. Thank you. So thanks a lot. So I have a question that is more general, and I would like to know if there's any positive things that one can do to encourage people to both do open data work and also to work on the calibrations, for example, of the data or the reconstruction of the data or the parts that are not visible in the final plot. Because I think this is necessary for experiments to want to release the data. Otherwise, they'll always be worried that someone is just skimming the cream out of the hard work that they've done. And there's this suspicion that we need to get rid of in order to make open data. So what's your suggestions?
Kati, would you like to answer? I think CMS has a nice example of how to deal with this.
I think, well, we are addressing these things. For example, I think it was mentioned by Phil Harris in his talk very well that there are certain things which are not yet still part of the release that we're doing, because simply we haven't had time to get them, say, scale corrections and that kind of things. But that's something that also with the time, in the scale of the LHC collaborations, I think it's something that arises naturally also if we think of ourselves. We will have legacy data which is also usable for ourselves when we have run 3, look back for run 1. And if we don't have all this additional information in order, not only in people's mind, but also in the way that they can really be implemented in the code, we lose them. So I think we're coming to that, with the time goes, we're coming to that idea also within the experiments, that data preservation, it's not just preserving data, it's really preserving a full workflow, as Tibor was saying. So I think the best is to have external people to use open data, kindly complain or make note that we don't necessarily have everything what is needed, and make sure that all the work that is done by external people on our data becomes part of the collective knowledge. So it's not that people who are working, we don't want it to happen again, that we build a community of external people who only know themselves what to do, but we really want to collect that knowledge and put together something that can be usable in many years to come. And that's something we want to show. And we also want to show that what is done with open data can eventually be useful also for people inside the collaboration. Just recording the knowledge, which is not obvious.
Mm-hmm. Yeah, that's an excellent point. I mean, you might want to, somebody might come up with a new theory 30 years in the future, and we might still want to look at the data that's available from these early runs, for example, and that it's fully analyzable. Yes, Philip, I think you wanted to say something.
So I have a kind of controversial follow-up on this, which is that there's a lot of merit actually to, working directly with theorists, or, at being on a collaboration, but then working directly with theorists or working with members on the other collaboration, all the way at the low level of data analysis. And if there is open data, you can kind of do this back and forth. But now you're talking about kind of interspersing the collaboration and open data analysis, which I don't think is as far as people have gone at the moment in terms of these open data policies. So like for example, if I were to do analysis with people outside of CMS on CMS data, I don't know if I actually could be an author. But this kind of, back and forth, I think there's a lot of merit to it. And I don't think it's, I understand this is controversial, but I think it would be a long-term, it would in the long term, it would be very beneficial for all of us to kind of just work with the open data freely. So it's something to keep as a point. I'm not sure where, what people are thinking about this in terms of actual policy.
If I may, I can comment on this. It's a very touchy point. If I'm a university professor and I know the data of Atlas CMS become public soon after the data have been taken, why should I then invest in the collaboration? I can use my research funds much more efficiently elsewhere there. And so basically it not only spoils our business model, but also the incentive to build the best instruments. much of that development actually happens in-house. And so I think the almost Solomonic decision that was taken by the Open Data Policy Group was to give it some latency. So the collaborations have the first stab at the data, and it comes with restrictions. You cannot jump boat and well, do publication with your own not yet released data, and also unreleased data of other collaborations. So it tries to protect the effort of those who actually built the instruments. And I have no, so looking at the financial point, one could probably find other ways of financing experiments. But I think what you lose is really the excellence that drives the whole endeavor. And that's something that I clearly wouldn't want to give up. So yeah, it's a touchy situation, very difficult.
Mm-hmm. That's a dimension I hadn't actually considered, that the funding is tied to having early access to data.
Well, you can also put it the other way around. These people are, they spend day and night to develop their instrument. They have a bright idea. They want to see that it works. They want to extract physics. And then, yes, they are convinced of their idea. I mean, an experimentalist doesn't stop by just showing my channel resolution is this and that. You want to show, well, and this made this branching ratio measurement possible. So I think it's really fair. Otherwise, the motivation is lost. And yeah, it's very clear. You can't go to industry and say, build us an LHC detector. It's just impossible. And this is why I alluded to astroparticle physics. There are some companies that are so close to the researchers that they actually can provide instruments that also model work very well. I'm still convinced that physicists could build a better instrument, but fine, let's leave it there.
Okay, so we are quite a bit over time. So Oliver, what do you want to do? I think maybe this is a good place to stop, and if people want to get coffee.
Yes, I think we can have a, sorry, Bruce.
I thought you left already.
No, I'm here. So yeah, we can have a 5-minute break so we can have some coffee and then continue with the panel discussion. Thank you everybody for this nice discussion, and also Nishita for the discussion chair.
My pleasure.
Yeah, we want to start on time because it's late in Asia. So we want to start at 4 p.m. Geneva time sharp. Thank you, which is 5 minutes to go.
जेवण छान झालं म्हटलं.
All right. Oliver has to go teaching, so I'm stepping in for him. So we're basically going to conclude the workshop with a panel discussion. And the panel will be led by Shufang Su. So all the panelists can now turn on their cameras. And Shufang, please take it away. Thank you.
Okay, it says I cannot start my video because the host has stopped it. Okay, let me try again. Okay. Okay, welcome everyone to the panel discussions. And let me share my only one slides. So this is just for an opening introduction. This panel discussion is aiming to discuss the communication between the theorists and experimentalists. And for those of you who were at the last session for the open access data, there are already quite some discussion there, especially during this new era of open access data. You know, which level of open access data should that be? And what the theory wants, what the experimental wants, they might be different. And there are also, you know, more social aspect of who is actually going to do the work and, you know, things like that. So that's what mainly this session is for, how to better facilitate the communication between experimentalists and the theorists. So let me introduce our panel members. Sally Johnson from Brookhaven National Labs, and she is really our Higgs expert. And Rohini Godbole from Indian Institute of Science, and she knows everything about collider physics, just ask her. And Yukin Kim from University of Chicago, and she is our experimental particle physicist, and she also knows about accelerated physics as well. Roman Sandra, our theorist, knows everything across the horizon from electric symmetry breaking to cosmic inflations. And Yifan Wang, and as from, oh, I forgot to mention Roman is from University of Maryland. And Yifan Wang is director for Institute for High Energy Physics. And he led his team experiments to measure the theta 1-3, and he also strongly pushed for the future colliders in China. So the format of the panel discussion is going to run like this. In the beginning, each panelist will have like about 3 minutes kind of to make an initial statement, and then we will open the floor for questions and comments and things like that. Okay, Sally, why don't you start? I'll stop share.
Okay, so let's see. Do you have my screen?
Yes, we do, but it's blank.
It's blank. Okay.
We saw your slide for a second, the first slide, the only one.
Yeah, I only have one. So where is that?
It was there a second ago. Just do
what you did and go back one.
All right. Let's stop sharing and start sharing again. There we are. Now you see it, right?
Yes.
Okay, so apologies for that. I just have a few simple thoughts about looking for BSM and what we might want from open access. I think Nima set the stage in a very, very good way in pointing out that we have no idea what we're looking for. There's no target. We don't know what scale we're looking for. We don't know if we're looking for a particle. We know nothing. So that says that we have to search broadly, which is an obvious statement, but I think it actually has some implications that we might want to discuss here. Because if I'm looking for new resonances or doing precision physics data, it could be that there are different strategies for preserving the data depending on what I'm going to do with it in the end. So for example, my particular interest is looking for precision measurements and comparing them with standard model theory and effective field theory. And I suspect that this will require different ways of saving the data and correlations and so forth. So I think we should keep this in mind as we go forward. And my last comment, in my 2 minutes I have here, is that I think the coordination between theorists and experimentalists is really crucial, because quite honestly, I can't see a lot of theorists going after this data and doing analyses with a team of postdocs. What I see is that theorists will connect with experimentalists who really know how to use the data and be able to do some analyses. So, next person.
Rohini, why don't you go next?
Try to see if I can share my screen. That's always a problem.
No, it was just me, Rohini.
No. Okay. For once, no, it's always for me excitement. Okay. So actually, thanks to actually the entire session that happened just before, and also to Sally for setting out things so clearly. So what I'm going to say more or less begins where Sally has left. So I think that just fine. So I think we all would agree that we are looking at this in the background of the fact that LHC has just performed exceedingly well. And there are two aspects that we want to see as we go forward. And one which is already mentioned, as mentioned by Sally, some of the people would want to measure to high precision some SM processes, which have been also computed to high accuracy. So really this is high precision meets high accuracy, and use that to probe the BSM. And the discussions to get the most out of the LHC data towards that aim has been, to some extent, has actually led to the ideas about recasting. I mean, I remember the years when these discussions happened, beginning in Les Houche workshops. And actually yesterday's talks showed us very clearly how the machine learning and things like that will help us on this path. And how the community wants to move on this aspect seems a bit clearer. What data are needed is quite clear conceptually, and how to share the data, and which data to share are the practical questions, more differential, what differential, and so on and so forth. And clearly, I completely agree with Sally that as a theorist, I always would finally trust only the experimentalist to tell me whether I'm mucking around, with the data properly. But I think political physics community has taken quite pioneering steps, and these discussions here to increase the interaction between the experimentalists and theorists in this context is sort of, at least the way is conceptually well defined. The other one is something that already was mentioned by Tao in his comment after the talk by the other earlier talk by maybe by Tibor or by Felix. And here the sort of completely new signatures, because we heard from Eckhard and all the people that, okay, experimentalists define objects and they will give us things in terms of those objects. But sometimes some unexpected signatures might have some different kinds of objects. And the point is to somehow discuss with the experimentalist and try to figure out how data about such objects, and one of them was yesterday mentioned about the backward moving objects. And here I would like to say that, yes, we have had actually a good interaction of this variety in the past few years through the different fora. And LHC detectors have actually shown us that they are highly versatile. And these interactions between theory and experiment has brought out entire new fields, such as LLP, or led to new dedicated experiments such as Mathusla and Phaser. So I think what we want to do is really now also a discussion, not just about how to share the information, but what extra information we would need if there are some unconventional objects, as it were, that we want to keep it for future, if perhaps those objects are not the most interesting objects right now, But who knows, in another 5 years, we might have some interesting theory where those become the most interesting objects. So this is about the data. But I think another very interesting idea that has emerged in this meeting, and I think we should really maybe take it forward at the end of this meeting in terms of whatever white paper and so on that Bruce and company want to bring out. And that is to do with the fact that let us have a repository of the anomalies and the constraints on the effective operators. And I think setting up sort of some group of people which begins to look at how jointly experimentalists and theorists, and I think we also actually need some help from the astroparticle experimentalists here, that could be actually setting up some kind of a repository or making a beginning with that, can also be one of the results of the meeting, or that is also something that needs to be discussed further, and we can see where it goes. Thank you. This is it. Onwards to, I think,
Thanks, Rohini. Young King, do you want to continue?
I don't have slides, but I'll say a few words. First of all, sorry that I'm not showing my face. I'm in a lecture hall. I'll be giving lecture in about 50 minutes. So that's why I'm wearing this mask. First, I would like to thank Eckhart and all the CERN leadership for this tremendous initiatives. They started with Scope 3 and was very successful. They made all of us to make it this open access possible. So it's a tremendous effort for them. And then now open data, this is a huge challenge as we heard, but I think it's very important, and this to my mind is the right thing to do. I think we are responsible. We have a responsibility and duty to make the data open to the public. And people talked about cost and etc. But I think the public, therefore policymakers, etc. They recognize if you make our data open, that means probably that we may get better support. So again, who knows? But I think it's the in the end, it probably a right thing to do, and maybe there might be additional support because we are doing this effort. So I hope that's the case. I really resonate to what Sally and Rohini said about all the connections or interactions between theorists and experimentalists. That's a key. So for me, one thing that I like to see more is before the open data, which is about 5 years after the data taking we are talking about roughly. But even the publication that's happening now, I really would like to see more enhancement. There are a lot of the interactions going on between experimentalists and theorists, but it'll be, I think it's more important to do even more. I hear a lot of comments from our theory colleagues that any published results or public information to our community, it's very hard for theorists to decode, applying to their models or something, even based on the published results. So perhaps the even the analysis process now, much before open data time, I would like to have us more proactively working with phenomenologists and theorists to find out what kind of information should be public, again, as a part of the public publications or the approved plots and numbers and etc. So I think by doing that, we will get a better understanding of how the theorists can use the open data. So for format of our open data, I think that we discuss a lot. I would like to see more of our proactive connections through the analysis time. Thank you.
Thanks, Yonki. Raman, wanna go next?
Great. So I'm just going to echo in my own words, I think several of the things we've already heard. this thing is pretty self-explanatory. As the theoretical arts and the experimental arts slowly evolve or rapidly evolve, finding that intersection, which is the best motivated kind of physics to hunt for, changes. And we need to keep shifting our gaze in some sense to do the most motivated searches. In that sense, we sort of have two lobes of our joint mind. And it, you know, obviously we would like to facilitate communication as best we can between those two lobes. I think speaking to people on the experimental side, and certainly as a theorist, we sense that it's not a perfect communication that exists already. I think one of the things that open access gives us is it gives maybe a way of introducing, especially the theorists, but even kind of the brainstorming experimentalists, a sense of the complex environment that the Hadron Colliders present. And what are the opportunities and obstacles, detectors and backgrounds? Just as an example, recently I wrote a paper with my colleagues on a kind of axion that would be a long-lived particle, and trying to even gauge the kinds of backgrounds for these long-lived particles, in other words, fake long-lived particles, is a tricky thing, which we don't really have access to. We had to sort of figure it out by reading other existing experimental papers and guessing a little bit what we were dealing with in these complicated environments like the LHC. Related to that is sort of just this job of recasting existing published searches to hunt and constrain new models. We tend to do that by looking at the two-dimensional papers in which, you know, PRL papers where things are listed. But in a sense, in the 21st century, you might think that there is some sort of notion of multi-dimensional publication, that there is some digital way in which we don't have to get everything into a two-dimensional plot. This may already be at some level of sophistication, but presumably there's more one can do in this direction. For theorists, it's sort of like you have new models, and this is a model, this is a signature that came up several years ago at the beginning of the LHC, where we wanted to combine a search strategy, which was a bump hunt, plus a kind of cut and count for leptons, but that was not being done at the time. And the question was how to get the information on what the constraints would be. So it's really a matter of recasting that I think is an art. It's going on and will continue to evolve. There are also processes that are sort of what you might call exciting in themselves from the standard model point of view, and also backgrounds to searches for new physics. For example, jets and QCD physics are very subtle processes, which we are, again, evolving in our understanding of. And by having real data, theorists and the analytic experimentalists can play maybe more efficiently with the real data in testing theories of their understanding of even the standard model itself. So the Lagrangian is known, but how to analyze it efficiently is not. I also imagine that this is sort of a open access gives a kind of marketplace for new models and strategies where outsiders in some sense can do kind of what I'll call amateur searches with unorthodox processes and or unorthodox search strategies, maybe involving machine learning, whatever. They probably will do a fairly imperfect job, but maybe there's some way that experimentalists can pick up on some of these amateur efforts and turn them into professional grade searches and analyses, but with greater creativity in that sense. The last thing I'll say is there's a third intersection here, which is with society, and really we need the support of society, but that partly depends on their level of interest. So the last thing I'll say is we take it for granted, but we have to remember that combining E equals mc squared with quantum mechanics is the creative process in nature. Literally, if you give me the right energy budget, there is a probability to create anything. And we're using that as explorers, even if we are at the boundary of the standard model, we don't know exactly what to expect. We are exploring the creative process, and we're trying and we're trying and trying and seeing what comes up. So it's really a kind of magic. And I don't think this is completely well understood by the world. Again, to some extent it is. It'd be wonderful to have the ability for school children or adults and so on, for the general public to play with what I really think is an alchemical process where we recreate things or create things for the first time since the Big Bang. And I think that will help support our subject. Thank you.
Thanks, Romer. And the last, Yifang.
Hello, can you hear me?
Yes.
I have one slide. So Raman, can you please stop sharing? Yeah.
Yes, let me stop share. Good. Done.
Can you see my slides?
Yes.
Yes.
Okay, so we all know that we have no signals yet. However, there were always some false signals at 2 to 3 sigma level. But we often laughing at this 2 to 3 sigma levels of signals, but we have to remember that the real signals often start to appear at such a level too. So we have many examples like neutrino oscillations, CP violations, and even Higgs, so on. So we probably have to be serious about the hints from current and maybe even the previous experiments. We have to make sure that we don't miss them, not only for us, but also for the community. So the signals may just be at the corner, just like what Nima said on the first day of this workshop. So we have to try our best to have more generic searches, search strategies. And also we have to have a more, say, comprehensive theoretical predictions. Of course, we have to employ new technologies like machine learning, AI, multi-dimensional fitting, and so on, as we heard from this workshop. And probably had to invent or try to come up with new ideas, new detectors, or the new proposals, just like people have been talked about, like axions or neutrino double beta decays and so on. Of course, we have to try new approaches like the open data. A lot of people have talked about this. Of course, this is a very difficult issue, but I believe that the sooner or later, one way or another, we have to do something very similar to the astronomers. Namely, we have to open our data to the public in a limited way, and we have to try our best to, on the one side, to preserve the correctness of science, the data, and on the other hand, we had to encourage normal people being able to use it. So I think it is a huge challenge for us, but I think it's hard for us not to do anything. Of course, all what we did has to be prepared for the next generation experiments. All the experience we had now and also in the past are all very, very valuable. We had to think about how to design new detectors. For example, how to get larger acceptance, higher efficiency, lower backgrounds, better resolution, and also try to have no cracks and holes in our detector. Also, we need to have, say, new technologies. For example, having wireless data transfer to avoid cable holes, and also higher, say, energy accelerators, the new machines, the lower energy detectors, lower energy threshold detectors, and also larger detector mass for, say, neutrino physics. So that's all what I have. And we certainly have a huge challenge ahead of us, but we have to do it together. Thank you.
Thanks, Yifang. So now we will open the floor for general discussions and comments and the questions. and there are already a couple in the Q&A part. So if the people who pose a question is in the audience, I think it will be better they can just ask their question themselves. Okay, so the first one is from Scott Gordon. Can we unmute him? And Scott, you there? Then you can just directly ask a question yourself. Has Scott been unmuted?
Can you hear me?
Yes.
Oh, great. Okay. So I want to address what Sally implied, that we really don't know what we're looking for when we're going through all this data at the LHC. And I'm wondering if anybody ever considered the fact that no matter what data we get from the LHC, that it will never expose the physics beyond the standard model. And then to address Raman, how, this is a collaboration between theorists and experimentalists. And what if a theorist comes up and says that he figured out why the LHC can't expose the data, why the data can't expose the physics beyond the standard model, and it's consistent with all validated physics, how receptive would the physics community be to something like that? Because it would just throw everything off track. So that's my question.
Thanks, Scott. I will let Sally address it first and then Roman.
Okay, so you say, what if we never find any new physics? By that, I think you mean new signatures or new resonances. And yes, if we don't find any new particle or new signatures, personally, I think the only way to go is precision measurements. Just measure, everything you can as precisely as you can, and have the theory as precise as you know, and then compare with some effective field theory model. And it's very, very hard. But that's the way we have to go.
Yeah, but what if that, at the end, what if it just never really produces anything?
Well, it's
that's a lot
going
of
to produce.
Faith to have.
Well, it's going to produce something because you're going to have these measurements, which if they agree with the standard model theory to whatever, precision, that's beautiful. That's a great discovery, a great triumph.
Well, and that's true, and that's true, but you didn't get beyond the standard model.
It's okay. That's okay. It's still beautiful physics in the same way that LEP was beautiful physics.
I understand that. Yeah. Okay.
Yes. So I'm good with that.
Okay.
Okay, Raman
might have a different.
Yeah. I guess I have a few slightly different thoughts. When you say, I think the question you addressed to me was, suppose a theorist had a theory where it explained that the LHC would never go beyond the standard model. So there are various interpretations of that. One example of that is the theory called the standard model. And if you just say, that's my theory, I'm a theorist, and that's my theory, then of course you won't. So it really is sort of with what level of confidence that theorist expresses such a thing. The idea that it's only the standard model has got some adherence from people that believe in the anthropic principle, which I think is a kind of, at the broadest level, a self-evident principle. But at a narrow level, it gets into various kind of implicit
philosophical areas.
Yeah, well, maybe I will just say it gets into various levels of assumptions that go in, and then you get the conclusions out. But one of those is that the standard model is here to stay for a hierarchy of energies beyond LHC reach. And again, so you're asking how welcome is it to hear such things? Well, when those ideas were put out in the early 2000s, that maybe the anthropic principle undermined our expectations for new physics, there was all hell breaking out, at least in the theoretical and experimental circles. People were discussing it, they were worried. I think it's disturbing. I would say none of these cases were ever well made. And so I personally don't have any example of a well-argued case for why the LHC will not see something new beyond the fact that the LHC has been running for this long. But if you ask, if somebody came and said, look, here's my really good argument for why you're not going to see anything, and if it was a really good argument, yeah, it would pull the rug out from underneath most of us sitting here. So it's just that that's a very hard case to make. People have been thinking about this for a long time, and there is a perfectly good chance that in the years to come, we will suddenly see, with low rates, a spectacular long-lived particle, which we can now see, and then suddenly the world changes. So when you're hunting for gold, I would just say that's the excitement of it, right? I completely agree with Sally, though, that if we don't see anything, our job is to do our damnedest to record and articulate that it's a high quality no, because that is a scientific triumph in itself. It may not be, different people will have different emotional reactions to it, but that is high quality science. And we need to articulate that as best we can. And even have the kind of legacy data to sort of allow people to go back and say, well, maybe it was hidden in a funny way, or maybe our theory got better. Standard model theory got better. In 10 years, we go back and we say, wait, we thought we had a high precision confirmation of the standard model, but it's not actually true. There's some, in this new way of looking at things, something is up. So that's kind of where I am. Personally, I'm also somebody for humankind as opposed to just my lifetime. I think there will be experiments that can be motivated and done beyond the LHC. I think we should think in those terms. There are experiments in gravitational wave cosmology that would complement future colliders. There are experiments in cosmology that would complement future colliders. I think all of that's very exciting. All of that's yet to come in the 21st century.
Thanks, Rama. And I see Yankee has your hand on. Do you have anything to add to this?
Yeah, I have some comments following the precision measurement comments that Sally mentioned, and also Raman said that as well. Since we are talking about open data, and we discussed a bit earlier, precision measurements like WMAS, Atlas, for example, it's this run one data is just we have the measurement, so it takes a long time. And that's one thing, but if other kind of precision measurements, I mean, those, understanding systematic uncertainties, and also not only that, we say, we have a better understanding, and some other areas, systematic uncertainty need to be improved, and etc. So those precision measurements, open data, it'll be huge challenges. So it'll be good to think ahead, all those things that beyond what we have been thinking about for precision measurements, we may have something to think about to make sure those things are well captured. So that will be challenging, but there's something to think about.
Thanks, Yankee. So we also have a couple more comments in the Q&A. Can we let Joey Huston in so that he can voice his comments by himself? Okay, cool. Joey, do you want to unmute? Cool. Yeah, go ahead.
Sure. So I posted a couple of comments in the chat giving examples of collaborations between theorists and experimentalists. So the first, and I think perhaps the paradigm for this, is the CTEC collaboration founded by Wookie Tung. And there we've had long-term collaborations between theorists and experimentalists for the case of the parton distribution functions going now on 30 years. Of course, that's not going to happen for most topics, but it is possible to have intense involvements between theorists and experimentalists. And as Rohini raised when her discussion, one of those examples is LHC, which has an intensity to it, right? And that's the problem with, I think, a lot of, such collaborations is that, do you really have the intensity to finish, a project? And with LHC, part of that comes from having to, live and work with people for 10 days and then carrying on for the year after that. Right now we have the snowmass exercise, which is very broad-based, but doesn't have the intensity of LHC, perhaps because of its longer time scale. I think something that hopefully will lead to success is trying to couple, for example, LHC and SNOMED, which is something that we're very actively trying to do since we're both interested in the same physics topics. Maybe if I can make another comment, which is that in the chat I raised the experience of Jesse Thaler in very successfully, being able to look at open CMS data, and publish physics results from that. And Phil Harris pointed out that he had the very active collaboration of CMS experimentalists to the point where they certainly would have qualified as authors on the open data publications if CMS had allowed that. I don't know what the Atlas policy is for something like that. We certainly don't have the type of open data model that CMS has, but that would be something I think that would be very useful, is to lobby the Atlas and CMS experiments to allow such collaborations to lead to joint publications.
Thanks, Joey. Yeah, Rohini, go ahead.
I basically just wanted to sort of continue where Joey left off. I mean, I think one of the important point, and which is what I tried to raise in mine also, that one has to develop sort of formats where this interaction can be more fruitful than it has already been pretty fruitful. And one of the reasons, for example, LHC worked is also because there was no experimental, in a discussion, you have also worked there. People from different experiments and theorists all were together. And that is sort of that kind of blueprint of interaction is what I have in my mind. And perhaps open data could help us achieve it if it is done properly. And the second point, this is all to react actually some comments that were going on in the chat. So I thought I will reinforce that point, is that it's actually very good. I mean, actually particle physics, I think, is much better than many other disciplines. We have been pioneering in doing many things, first. And this interaction between experimentalist and theorist, even though we are complaining, it's not been bad. I mean, it's pretty unique actually in high energy physics that experimentalist and a theorist runs a session. It's very common in all our ICHEP sessions or whatever. I think this whole discussion is to really see how we can take it to the next level so that we can get the most out of this frustrating data, large amount of frustrating data.
Thanks, Rohini. Yeah, I think Nishita actually have some comments along the similar lines about collaboration policies and things like that. Nishita, do you want to just speak for yourself?
Yes, thank you. So actually building up on what Rohini just said, and also what Joey particularly mentioned about having the possibility of writing papers together for theorists and experimentalists. And this seems to be a major issue that we are wrestling with right now in the long-lived particle working group. So one of the things that we want to work on is trigger strategies for the future, because one of the main problems with long-lived particles is that the triggers don't exist to catch this kind of unusual phenomena. And of course, theorists can't do this by themselves because they don't know the detector well enough. And the experimentalists want to help, and there is actually a document ready to be disseminated. However, we are running against collaboration policies about such a document being made public or publicly available, and what it means about giving credit where credit is due and so on. And also possibly about releasing internal information before it has been vetted by the collaboration. So there are lots of such issues that are going on in the background, and it's not entirely clear how these things can be solved. So in certain working groups where they deal only with process data that has already been given out by the experiments, these problems don't come up as often. But if we want to, like Rohini says, take it to the next level and actually have a dialogue about these more deeper issues, then we might have to think about how this can be made possible.
Thanks, Nishita. And okay, Biswarap, you have a question to ask? Oh, oops, sorry.
Yes.
Rohini
Yeah.
just raised her hand. I saw she has some immediate comments back to Nishita's
Yes,
comments.
thanks,
I'll let
Shivang.
Rohini go first.
No, I just wanted to say something that it's not that one should, I think there is a lot of strength when a collaboration comes up and supports something that a theorist has suggested, because the collaboration has not only the strength of the numbers, but also the knowledge, the intuition that these people have got about what the detectors do and what the data mean. So I think a theorist really wants to profit from that intuition and that understanding. And somehow it's a social question, how we can do it. But I think that's where, otherwise we are missing out on that intellectual input from both sides.
Thanks, Rohini. Nice comment. Yeah, I think the challenge is really how to get those information passed on, which is not an easy task. Okay, yeah, Biswarap, do you want to unmute yourself, ask your question?
Okay, so what I'm going to say may sound a bit defeatist or pessimistic to start with, but actually it is more in the way of soul searching that I'm saying this. Of course, we are all somewhat desperate that nothing in the way of new physics is coming in experiments. But if we look at it historically, then the first, so to say, near perfect theory, or should I say perfect structure that came up in fundamental physics, in a way was Maxwell's electrodynamics. And as we have seen, after it came into full shape, which I believe was 1868-ish, we had to wait for about 37 years before a paradigm shift took place, and we had the first 30 years of this previous century that shook all of physics. Now, what I'm trying to say is this: with as simple a thing as Maxwellian electrodynamics, simple in the sense of economy, we had to wait for 37 years or close to 40 years before the next paradigm shift took place, next breakthrough took place. On the other hand, we have been developing something much more complicated and multi-directional like the standard model. And to be very frank, the last vestige of confirmation came as late as in 2012. So I'm asking a question: are we being a bit too impatient in our effort? Now, I think the overwhelming majority will say no, myself included. But in case that is the situation, can we expect guidance from the experimentalists? And here, can this open data guide us towards some, if not paradigm shift, complete different ways of thinking as compared to what the many directions we have been thinking of in looking for physics beyond the standard model? This is all.
Thanks, Biswarap. So this question is addressed to experimentalists, and I see it's midnight in Yifang's time. So,
Yeah.
So who of you want to pick it up?
To experimentalists. Because I know what theorists will think, and I think pretty much the same way. But how the experimentalists think, do they think we are being too impatient?
Yifang, go ahead.
I'm actually falling asleep, so I'm not really sure I can say things so smart. I believe that you're right, and we are not patient enough. And although we have been trying to see new signals as soon as possible, but in fact, big discoveries may happen and should happen in a longer waiting time. So I think we just have to be patient enough. And on the other hand, if you look at the signatures or the energy scale covered by all the searches at LHC, I think at the 1 TeV not seeing new signals is not a big surprise. If we don't see new signals at 10 TeV, I think then we have a big surprise. So I'll say if we see new physics at 1 TeV, great. But if we don't see it, it's not a surprise. So be patient until 10 TeV.
Thanks. But is there any reason behind this magic number 10?
No, I mean, it's just a round number. Of course, we cannot talk about the 11 or talk about the 7. So it's just a round number.
You mean an order of magnitude?
Let's talk about 13 and 14. Okay. Yankee, go ahead.
Yeah, so just following up what Yifeng said, to my mind, I think it's very important that our community and broader scientific community and those who are working on this breakthrough in technology. If you look at talking about the accelerator collider energy, we are not going as fast as we used to going up. So if you think of all our discoveries and etc., we heavily rely on all the tools, accelerators, detectors, all this. Whenever you have something breakthrough in technology, we get something out. I think we have. I'm very concerned about that. That's why even if I'm not an accelerator physicist, but I get involved in and recruiting more students to work on it. I mean, it is an issue. As an example, accelerator. We have even US alone, hundreds of students per year we were producing PhD. In accelerator physics, it's about 20 per year, entire US. So if you don't put brains in this, in this technological breakthrough, technology breakthrough doesn't mean just like engineering. You have to have fundamental science breakthrough to make jump. So I feel like we have to pay a lot more attention to accelerators, detectors, instrumentations, and computing as well. That really made us really jump and new discoveries. So I feel like we are a bit unbalanced, and how much of our community putting on the technical development versus doing analysis. So I really hope that we have a better balance in the future.
I completely agree. For example, with this laser plasma accelerators being appropriately used, Yifeng's 10 TeV as assurance may very well become 100 TeV in no time.
Absolutely, yeah.
Yeah, I agree completely. Thanks for the observation.
Raman, you have your hand up.
Yes, thanks. So I guess related to this question of, or hand-wringing regarding when is the new physics going to show up and so on. Of course, we don't have an absolute foreknowledge of when it's going to happen and whether it's going to happen on LHC watch. But I don't want to say that we are actually devoid of how to gamble. That is, I think theory does actually provide a lot of guidance on how to gamble, because it's guided by the grammar, which is very, very tight, called quantum field theory. It's like the rules of chess. When I say it's tight, the rules of chess are tight. They have a lot of games, but you can't just do anything you want, right? So I think, for example, understanding how precision tests constrain new physics, understanding how flavor physics constrains new physics, understanding that there are these portals that are the most opportune way in quantum field theory to get into new physics sectors, like the Higgs portal. The fact that the Higgs is not just the centerpiece of the standard model electroweak symmetry breaking, it is also, for structural reasons to do with renormalizability and so on, a very good bridge into other sectors, so that looking for exotic Higgs decays with long-lived signatures, it's not some desperate last-ditch thing that we thought of. It is one of the sort of best places to gamble in these ways. So I would say that we are detectives. We're trying to solve a whodunit, if you want, and there's lots of guidance from theory on how to do it, and we are pursuing a lot of those best bets. It's not a completely random process. We may get surprised, but there is a kind of method to what's going on. I would say we don't have a guarantee that the LHC will find something, but a lot of us are actually asking, there are some kinds of searches at the LHC where already the data is sort of constraining where could a gluino lie? Okay, well, the data is largely in, but there are other kinds of things. LLPs are classics where the room for discovery at the LHC is enormous. So we are being guided by what I'll say is, where are there big chunks of room where the LHC can make discoveries, and where are we sort of slowly asymptoting to the end of what the LHC can do? I think all of this can be intelligently pursued. It is being intelligently pursued, and all of it, I hope, is setting ultimately a place for future colliders and completely non-collider experiments like direct detection of dark matter, gravitational waves from first order phase transitions. We need to have a lab in which these other experiments can be studied if they bear fruit. So that's my hope for the 21st century.
Thanks, Roman, for the comments. Eckhart, you have a related comments? Go ahead, unmute yourself.
Yes, I have. Yeah, thank you, Roman. I basically want to chime in with what you said, and maybe slightly different words, because the progress on the energy frontier with the LHC will be slow. We know this. With more luminosity, you push out a little more in the X of the colliding partons, and that gives you a little more effective energy to study. That's a statistical problem, and it will come to a certain point, and eventually we will run out of patience. What I'm more concerned about is some lessons from the past where the data were collected, but the signature was not found, not detected. And the ISRs and the folkloristic example for charm physics that was overlooked, B physics was also not everywhere detected. And that, I think, is the disaster. Are we not asking the right question and look into the data? And in this context, I think the open data approach is a very valuable one, because somebody just comes up with a crazy signature. You know, in the end, it's heavy ion data that in the complex final state reveals some interesting results. I don't know, but we must make sure with this joint effort on open data that we really look at the data from all aspects without any prejudice. And that I hopefully, I wish would help. Thanks.
Sure, thank you. Rohini, you want to make some quick comments?
Yeah, I wanted to chime in. You know, I mean, this is for what it's worth. I mean, we have not simply not looked at everything. Somehow we have looked under the lamp, the proverbial street light. And I mean, at low energy ends, I still think low mass ends, even, you know, we're not even thinking about sort of, even with these portals ideas, very often in the LHC data, things, even in the LHC data, not even heavy ion data, something might be lurking at low masses. It doesn't have to be the high energy tails. And that is where we need this real, and the point that Suchita was making, or Nishita was making, that this is where you need to have perhaps discussions about understanding triggering, understanding, you know, looking at the same data, but with different lenses altogether. And that's where this interaction between experiments and theories, experimentalists who understand it very, very well is really, really crucial. And I, for one, don't feel depressed that we haven't seen anything so far. I would have been happier had we seen it, but I think it's the name of the game.
Thanks, Rohini. Yeah, that's the purpose of this workshop, to look at those hidden physics over there. So we have Joey has been very patiently waiting. So why don't you unmute yourself and then you can talk.
This is just a brief follow-up to the previous comment that I made, that I stressed the importance of the theorist and experimentalist having a chance to work together at Les Houches, but perhaps even more important was the chance for experimentalists from different collaborations to work together. I've heard many comments, for example, from members of Atlas and CMS, saying that it was so great to be able to talk about physics and not about the pressures of trying to combine results for some, you know, conference or workshop or the other. So I think having a relaxed atmosphere like that, you know, is also very good, important for the advancement of physics.
Tao?
Yes, first of all, I would like to very much agree with the very clear, sharp statements by our panelists. For that, I thank you all. Looking at the title of the workshop, and I'm reading the hidden physics at the LHC, obviously we have to work hard and dig deep, in the sense that we have to look into all these small possible deviations, all the possible and even impossible signatures, and so on and so forth, anomalies and along the line, and also deep learning, trying to see we can dig out something from the hidden data and the machine learning and the open data and so on and so forth. Another aspect I want to emphasize that beyond digging deep, we also need to think broadening ourselves beyond the LHC. So fundamental physics usually reveals itself from a very broad aspect. So we also have other related experiments, such as flavor physics in the quark sector, and also neutrino oscillation measurements and possible connection with the electron sector. And more than that, cosmological and astronomical measurements in the observations usually give us a lot of possible interplay. In particular, these days, the gravitational waves, they just came as a shock, right? The gravitational wave measurements, you seem to be able to tell us some possible connection with the underlying physics, such as inflation, and also in particular, the electric phase transition, and so on and so forth. I think it will be important for us to also keep in the close contact from our view to think about the possible underlying physics beyond LHC and in a coherent way, and branching out into the other observables. I think that's our job. Not only we are LHC physicists, but also we just simply want to understand the nature. So along these lines, since I'm here, so I would like to offer my comment towards Scott Gordon's question in my own way. The measure of our science is not the failure or the success of declaring a discovery. Our job is to understand nature. Our job as honest scientists, we want to understand nature to the deepest level. We have understood the nature up to the TeV. It's 10 to the minus 18 centimeters. It's 10 to minus 9 nanometers. You think a nanometer is a small science. We are deeper than the nanoscience by almost 10 orders of magnitude. We honestly understand the nature to the deepest possible level. We are marching to the deeper level. We honestly understand the nature and tell our community and society what we have seen. That's our success. Whether you discover something or not, so that's along the way, okay? So our job, Scott, is to understand nature to the deepest possible level. That's our job. Okay, not really measuring yourself, discover one bump or not. Okay, so that's the thing. Coming back to Bishop's question, I think we are spoiled for being so successful for the past 50, 60 years. We have uninterrupted discoveries, one after another. That's great for our field, but we have to be patient to see how nature works. Again, our job is to understand how nature works. It's not how impatient, which year we hope to have discovery. We understand nature deeper. That's our job. So that's my statement about how we should proceed to march into a deeper understanding of nature.
Thanks, Tao. And given that we are close to the end and Yanqi and Yifan probably need to go, let's do some closing remarks. And this time I'll start with the experimentalist. So the question I pose is, as an experimentalist, what do you need the most from theorist? Definitely not another model. And then for the theorist in the panel, the question I want to pose is, what do you want from experimentalist? I know discovery, of course, but other than that. Okay, so is Yongki still here, or she need to go to her class? Actually, okay, then Yifan, you'll be the representative for the experimentalists. What do you want most from theorists?
I would say in one simple sentence, I want the theorists to tell me where to look for new physics and how.
So you do want another model, okay? We're useful. Thanks, Yifan. And now let me go in the order from Raman first. What do you want from experimentalists?
So a strange answer, but because I get a lot of what I want from experimentalists already. I think they're fabulous, and in a sense, I don't want to second guess them and say there's something even more. But here's what I want. I want more of them for longer. So I've said this a few times that I want us to proceed triumphantly in the 21st century doing sort of grand physics on a number of different fronts, including Collider. But Collider is the laboratory setting for fundamental physics. For that, I feel like we need the right culture and expectations of what is success. We've been talking about what is success and failure here. Is the standard model alone a failure? But we need to have the right exploratory spirit, which is going to have to cross a few experimental generations to get through the century. And I would like experimentalists to join with a sense of excitement for the fact that they can, do wonders perhaps, but they're taking a chance, that the risk is truly grand, and the rewards are truly grand. But how can they arrange themselves culturally so that students will join, be intellectually challenged, both on the hardware side and the theory side and the analysis side? I just want them to keep going. I don't want the field to die out.
Thanks, Rama. And Rohini, your turn.
I thought I said very many things that, but first I will echo Raman and all the others that I think, without echoing, I really think that our field has had excellent talking between experimentalists and theorists. But what I would like, both for experimentalists and theorists, young people, to get out of this mold, where, how should I say this, that a typical young experimentalist will give me a talk and say, I rule this BSM out and I rule that BSM out. But I think what I want to tell them is that what our friend Tao also emphasized, we want to learn about nature, and this is a wonderful instrument we have, and we want to take the attitude that we want to know what the data are telling us, and we need their help because they are the only ones who can. But I think all we want from them is to get out of this framework that we are ruling BSM out. That is not what you want to do. What you want to do is you want to find out what the data are telling us.
Thanks, Rohini. And Sally, you want to have the last word?
The last word here, how nice. So I'm involved in a number of the working groups with the LHC. And so what I really want from experimentalists is to keep being involved in these collaborations we have between theorists and experimentalists, that these are wonderful opportunities for all of us to communicate. It's a forum for CMS, Atlas, and theorists to all talk together. So what I wish from the experimentalists is that there's even more participation in these groups. As Joey said, Les Ouches, there's SNOMES. There are a number of forums where we can collaborate in a formal way. And so we need to keep working on these and strengthening them because they're what we have and they're wonderful.
Thanks, Sally. Okay, so the panel discussion is closed. I hand it back to Bruce. Hey, Bruce, you there? Cool.
We will have Oliver closing up. He's back from teaching.
Okay. I didn't see. Oh, okay, good. It's
Hi,
back.
now I can see you.
Mm-hmm.
Okay, thank you very much. Thanks all of you for these great discussions. This was, especially the wrap up now was really nice. So we didn't have to do it. It happened automatically with all these closing remarks from the panelists. I want to thank all the speakers from today's sessions in the first and the second session, the discussion leaders, in particular Shufang from the last session now too, all the speakers from the last 2 days. I think we had a lot of great contributions, talks, discussions, and subjects being raised. We should not have the discussion stop now with the end of the workshop. That will be quite abrupt. We still have the Mattermost forum. You can use it. We'll keep monitoring it. You can keep sending emails if you want. There are some interesting links and pointers for the future, like the forum that Tibor pointed out. We can also start using that actively. And as maybe the last closing remark, and Bruce may chip in if I'm forgetting something, is that we will try to provide a summary of what happened here in a written form that will be on the archive sometime in the near future. And if any one of you has a contribution to make that should not be omitted or forgotten, or maybe it didn't find its place into the discussion in the last 3 days, please also use one of the channels that you have and let us know about it, and we will try to also incorporate that if possible. Bruce, do you still want to say something? Or did I forget anything?
No, I think that's what we discussed. And I really want to thank everyone. Go ahead.
Perfect. And then maybe the last thing that must not be forgotten. So again, we are very thankful for this seamless operation of this workshop, which would not be possible without the Liverpool support team, in particular Russell and his crew, but also from the many people from Mitamba Labs and Witwatersrand University that came with Bruce's support to support Bruce and me. So thanks to all of you, and thanks to everybody who did a contribution to this workshop. It was a wonderful experience.
We cannot leave without thanking Oliver and Bruce for this wonderful effort.
You did this. I wanted to do precisely that. Yes.
Yeah, we must. Yeah.
Thank both of you for having run with the idea so well. You ran with the ball very well.
Clap for them. Let's clap.
Thanks, and thanks everybody from the organizing committee. It was a really good experience. Okay.
Thank you, guys.
Thank you. Now there is no travel back safely. It is just saying go back to whatever you are doing
stay safely.
with your day or the night as the case
Sign
is.
off safely, just a button away.
Some of us are
Bye,
going
guys.
to sleep and some of us are going to.
Thanks,
Bye.
everyone.
Bye, everybody.
Bye, everybody.
Bye.
Bye.